Welcome. So, yay! So, yeah, no matter how rational you can try and be, for me it's very hard to fend off the impression that today I'm crossing some very important threshold. It doesn't mean in reality nothing happens, but mentally it does, okay? And so in order to, if you want, exercise any possible bad feelings, you never know.
But it does.
Exile.
I want to have fun, so, and also as a sign of gratitude for the wonderful people of this department that has hosted me for this year, that for me has been very special because it's been very different than the years that I've gone through in the last 2 or 3 decades, where I was always worried about it. Here I was just focusing on physics. We will see what comes out, okay? Not yet clear. Anyway, so the fact that these two things came together, because of that I found it natural to organize this little event. One of my friends here remarked that this is like an autocratic fest, a sort of Bonapartean self-coronation. You can understand who the guy is. And, come on, this is just a birthday party, okay? A birthday party has 2 main elements, main ingredients, friends and a cake. In this particular case, there is no cake. The cake is physics. It's all for you to enjoy, so enjoy.
So, yeah, it's an honor to start the birthday party. So, I know Riccardo doesn't want to be celebrated, so I won't. Other people were mentioning the possibility of roasting. Unfortunately, many of the interesting things that Riccardo says cannot be repeated in public, even though he probably did say them in public in the first place. So I just want to devote 2 minutes instead to a personal memory, which, wait.
It's not a wave function normalization.
Which will also serve as a cautionary tale. So I was once upon a time, I was a young undergrad, drifting through life without much purpose or direction. And back then there was no Wi-Fi, there were no laptops, so we work in these big computer rooms. And one day I was working there, and there's a commotion, and there's a loud young man there, and perhaps not as young as this guy here, who's clearly up to no good, but something like this, maybe a couple of years younger than this. And this young man is struggling with a printer, and Riccardo being Riccardo, the struggling with the printer was pretty dramatic. There was some swearing and there was some physical activity. And so I was moved by his struggles, and so I helped him out, and we figured out how to print the paper he was trying to print. And now it's a universal principle of social psychology that humans go out of their way to repay even small favors or debts. So maybe because of that small favor that I made to him, over the intervening 25 years, Riccardo has helped me immensely to develop as a physicist and in my career, and even as a friend. I think now we're good, Riccardo.
You are good. Way too much. This is
You can't forget about the print.
I'll stop crying.
So the moral of this
I want some real roasting later. I'm sure it's gonna come. Okay.
yeah. So the moral of this cautionary tale is be kind to strangers, because you never know how important they might end up being in your life. So back to physics. So I want to tell you some recent work, now it's 2 years old, unfortunately. I did with Ira, who most of you know. And if I have time, I will also supplement it with some apparently unrelated, but I think somewhat related work I did with my students and postdocs. And so I don't need to motivate to this audience the importance of naturalness problems in particle physics and gravity. We have the electroweak hierarchy problem, we have the cosmological constant problem, and the smallness of these parameters is not enforced by any symmetry-based selection rules, and so many of us believe that these are problems. Perhaps not all of us, but many of us do believe that these are problems. In fact, Riccardo spent part of last week trying to teach us how to cleverly use selection rules to figure out natural values for coupling constants, expectation values, etc. And these two quantities maximally violate those expectations. So, what I want to do in this half an hour is to motivate this claim so that things like this, so these apparent fine-tunings, can happen naturally when we break some space-time symmetries, and I don't have a general understanding on when this happens, why it happens, but I was just to prove this claim by giving you specific examples of real systems, and by real and naturally, I really mean in nature, okay, without any intervention even from humans. My claim is that if you pick up a random rock, there is something that looks like a fine-tuning there. So here's the experimental data that support this claim. So if you take any solid, you know that when you push on it or when you pull on it, it will develop, it will reach an equilibrium state in which the internal stresses, particularly stress energy tensor, balances completely the external force that you apply. Let's neglect for the moment surface tension. If you're interested, I can tell you about surface tension, and I will show you that surface tension is irrelevant in the colloquial and technical sense as far as this problem goes. Now, if on the other hand we release the external pressure, so if you want, we remove the boundary conditions, we let the boundary conditions free, the stress tensor inside goes to zero. It relaxes to zero. And this is not enforced by any symmetry, at least as far as we know. This is just a relaxation condition that comes not even from the bulk dynamics of the solid, but from the removing of some boundary conditions. And perhaps even more dramatically, there is a fact that was known to many people, including Freivogel and Piazza, and I learned that from them actually, so I thank them. If you take a beam, and by beam or rod or bar, I mean any approximately one-dimensional solid, so much so that you can neglect in first approximation finite thickness effects. So if you let at least one boundary condition free, the dispersion relation for the transverse excitations goes like k squared, not like k. And clearly the symmetries of these are the same as the symmetry of a guitar string, which, as we know very well, when you have some tension, okay, the frequency goes like something like the square root of the tension times k. It's only when the tension can relax to zero, again, by removing a boundary condition, this one, that this coefficient drops to zero and you're dominated by an algebraic terms. Okay? And this is very well known. Okay? And however, again, there's no symmetry reason why that should be the case, or at least I will show you how symmetries come into play. So, so how do we understand these facts? So these are just facts. Okay? These are well-known facts, and there's nothing we can do about it. But how do we understand this from a viewpoint of quantum field theory and effective field theory? So let me first describe quickly how you can build an effective theory for the bulk dynamics of a three-dimensional solid, and then we'll worry about what happens when you have a boundary. So suppose you have an infinite solid, and what are the degrees of freedom that survive at low energies? They're essentially some Goldstone fields. And in particular, in this case, the Goldstone fields are can be interpreted as the comoving coordinates of the solid elements. So here I have some sort of jelly that is sort of moving and deforming in space. And I choose some coordinates that live in the jelly, they move with the jelly. they get deformed, the jelly gets deformed. So these are co-moving with the volume elements of the jelly. And the configuration space involves a mapping between the internal coordinates and your lab coordinates as a function of time. So these are your degrees of freedom. You have three scalar fields. They call phi I goes from 1 to 3, and at equilibrium, at some given pressure, let's say, or density, you choose your coordinates in a way that they are aligned with the physical coordinates of your lab. Up to a constant here, this measures the compression level of your medium. In fact, this constant could even be a matrix, okay, because you could rotate your medium, you could boost your medium, you could shear it. All these are equilibrium configurations of the same solid. But for simplicity, let me forget about these other transformations you could do to the medium. Let me just talk about the level of compression or dilation, okay? So now, so far we know what the degrees of freedom are and what the equilibrium configurations look like. And now we have to figure out the symmetries. Well, the symmetries are Poincaré. And then there's going to be some internal symmetries that we have to impose, because apparently this equilibrium configuration breaks a number of spatial symmetries, space-time symmetries. It breaks boosts, and that's fine because the medium has a preferred rest frame. But it also breaks translations and rotations. Remember, these are scalar fields. So in order for this to be describing in the long wavelength limit a homogeneous isotropic, or not even isotropic, but with some, let's say, even discrete rotational symmetry solid, you need some internal symmetries to compensate the fact that these expectation values break spatial symmetry. So in particular, you need shift symmetries to compensate for the broken translations, and you need some rotation symmetry. Could be the whole SO3 if you're describing a solid that is statistically homogeneous, could be some discrete subgroup if you're describing a crystal which has some preferred axis and a given symmetry group. And then, as usual, you build your action, variant under the symmetries, organize the derivative expansion, etc., etc. So the action happens to be the most general function that you can have of this particular matrix here. This matrix is invariant under shifts and is invariant under Poincaré because of this contraction. So now you want to impose the rotational symmetries of the solid, and so you want this function of this matrix to be invariant under the symmetry group of the solid under consideration. And the arbitrariness that you have here in this function, it's an arbitrary function, is the same as saying that the equation of state from the viewpoint of the effective theory is an input. You cannot predict from the effective theory the equation of state of a solid. It's an experimental input, or a theoretical input if you have a microscopic model that you can solve. And then you can look at excitations about the background configuration, which was this alpha xi. You parameterize it with some fields pi I. You expand the action, you have a kinetic energy, you have gradient energies for longitudinal modes and transverse modes. These coefficients here, Cl and Ct, are the propagation speeds. They are related to G and its derivatives on the background, but from the viewpoint of the expansion in pi, you can also take them as independent parameters. Okay? And this is well known. And if you keep going with the expansion, you can include interactions among the phonons. So these are the phonons, longitudinal and the transverse phonons. You have interactions, you have higher derivative corrections, etc. Now, how do we talk about the boundary in this language? Well, a boundary of a solid is fixed in comoving space. Okay? If you rotate or compress or deform a solid, as long as you don't break it, the atoms at the boundary are always the same. So the comoving coordinates of the boundary do not change under physical deformations or physical evolution of the solid. So a boundary, this is comoving space, for simplicity, I'm just looking at 2 dimensions. In comoving space, the boundary is something like a surface like this that does not change. Okay, so this is let's say, the effective theory of a potato. This is your potato in comoving space. The shape never changes. In physical space, it can change. You can compress it, dilate it, deform it, etc. So you can talk about the boundary in the action as the surface level of some function f of your field. Let's say when f equals 0, you have the boundary. When f is positive, you are inside. So your action with the boundary now is a theta that tells you have to be inside the solid to have some non-trivial Lagrangian density. And this function is a function of just your fields. Okay? And that's it. So now, free boundary conditions simply means that the variational problem is you vary your fields. Sure, you could impose, if you want, vanishing boundary conditions at infinity, but that doesn't really matter because you have this theta, so at infinity, really nothing matters. So you can derive the equations of motion, which are nothing but, if you want, the conservation of the stress energy tensor or of the current associated with the shifts. And and let's just look at the static configurations. So in the bulk, you get that all components of T mu nu, in particular Tij, must be constant. And so in particular, it tells you that a configuration like this is valid, obeys the bulk equations of motion for any alpha, simply because Tij depends on derivatives of phi. Okay, so if phi has a solution like this, derivatives of phi are constant, and so Tij, which only depends on derivatives, is constant. Okay, but at the boundary now, this equation of motion, when this derivative acts on the theta, you get a delta function. So you get a boundary equation, and the boundary equation for static configurations tells you that Tij projected onto the normal to the boundary must be 0. But Tij inside is constant, and so when you explore that boundary equation by varying your n along the surface, you can explore all possible directions. So this means that if you combine these two equations and you explore all the directions that you have normal to the surface, you get that Tij must be 0 everywhere. This is an equation for alpha, if you want, for this parameter. Okay, so alpha will adjust the level of compression or dilation. You suppose you to start with a very compressed solid, you let go. The level of compression will adjust, perhaps dissipating some of the vibrational energy, until you reach an alpha that satisfies this.
Alberto,
Yeah,
this is assuming that you add no boundary term in the action.
yeah, I'll talk about that later. You understand? Okay, I claim that those are irrelevant in the sense that for a macroscopic solid, they are a surface over volume effect. So the bigger the solid it is, like for bubble expansion, nucleation, etc., it's exactly the same effect. But I can give you some more precise estimates later. But you're right. It's neglecting surface tension effects. Okay, now I could, by the way, another way to see the same would be to go back to this action. Here, input, just do a reduced variational problem in which you input your ansatz that phi is alpha times x. You input it here, and what you get is an effective potential for alpha. And minimizing that effective potential for alpha is exactly the same as this relaxation condition. Okay? So now, by the way, this tells you that alpha must obey a very specific condition. And if you were to plug it back into the action for perturbations, you might ask yourself, okay, does this enforce some cancellations here or some apparent fine-tunings? And at this level, you can, because these parameters here depend on alpha because they depend on derivatives of g evaluated at this specific alpha. Okay, so in particular, there could be some.
What are we relaxing towards then? We're relaxing towards what value of alpha?
Well, it depends on the equation of state, but it's a value of alpha.
It's a value of alpha. It's some
such that this is obeyed.
I see. Okay. So this is not like the axion, for example. I mean, there something is dynamically relaxed, but there is something special about the place that you relax to. Like theta equals 0 is special.
Parity is there, is the parity
is there.
special.
Yeah, that's what I'm asking. Is the place where you is there a symmetry you can associate with the place?
Apparently not.
No.
Apparently not.
By the way, in your bar, are you going to do Gordio? Sorry, go ahead.
Yeah, let's talk about the bar.
Yeah.
So what happens instead, if I now take the dimensional reduction of the dimensional solid down to some elongated solid, or for simplicity, I can just write down the effective theory directly for the one-dimensional solid. Okay? So I take a one-dimensional solid, and now I do essentially string theory. So I have some embedding coordinates and functions of worldsheet coordinates. I have another scalar field that lives on the worldsheet, and this is the same as the solid co-moving coordinates that I had before. Without this, I would get a relativistic string, a relativistic bosonic string. So I need another field somehow to say that I'm describing a solid and not a relativistic string, fundamental string. And sorry, this would be d tau d sigma, not d tau d tau. And then I do the same. I have an action that is a generic function of some invariant that has to do with the derivatives of my solid field, the induced metric, etc. Square root of g, of course, to have everything invariant under parameterizations. And then a theta that tells me that when I go past a certain value of phi, which is the co-moving coordinate of the solid, let's say phi star, the action starts. Okay? The solid has a finite fixed extension in co-moving space. So the ground state, I can do the same analysis before, but now it's slightly easier because there's only one solid field. I can use unitary gauge if I want for time and x1. The ground state will be x2 and x3, so the transverse directions equal 0, so I have a straight bar. And the solid field will be the same as sigma times some level of compression or dilation. And again, I can do the game of plugging these ansatz into the action. That gives me an effective potential for alpha. And you get that, depending on the equation of state, sometimes this equation relaxes to a specific, this equation has a minimum, this effective potential has a minimum somewhere, and this relaxes your value of alpha to some alpha bar. Again, not associated with symmetry. If you change the equation of state of your solid, you get a different alpha bar.
Okay, so it's very intuitive because, I mean, if you push it up or down, it's kind of a parabola, right? It's not going up and down, sort of linear. Well, let me ask, if you put the whole thing in a big, like, gravitational field or something so that the equilibrium position of the bar was already shifted down, do you know what the fluctuations around that would look like?
I think you will get a little bit of a
K.
And
So
I'll show you why.
Okay.
I'll show you why.
So
for now,
so this is, you're sure this has nothing to do with the reflection symmetry around the, that's kind of what it looks like, is that?
a reflection symmetry around the
Yeah, around the bar.
It has to do with this, so I'll show you. It has to do with the fact that you relax to zero tension. Let me show you why, okay? Because the minimization of this effective potential, you can check, is equivalent to the vanishing of T sigma sigma on the worldsheet, okay? So zero tension, if you want. So the reason this enforces directly the vanishing of the gradient energy for the transverse modes is this. So if I now, still in unitary gauge, if I now perturb my fields, so my phi is my sigma plus a small perturbation, and the transverse coordinates are just the perturbations, well, I know that the x mu fields enter the action only through the induced metric. That's the only way they enter the action, okay? And the induced metric is flat plus quadratic in transverse perturbations, okay? So now, the quadratic action for the perturbations is nothing but the linear variation of the action with respect to the metric, which is the stress energy tensor. So whenever you relax to a state of zero tension, the quadratic gradient energy of the two derivative gradient energy of the pi's is zero. So this relationship is enforced by symmetry. Okay, the fact that the induced metric and pi are related in this way is enforced by symmetry. But the fact that you relax to zero tension is not enforced by symmetry. Now you might say, okay, what about, but if you break parity, maybe you relax to non-zero tension, maybe. But you see, but on the other hand, if I give you the guitar string, you don't relax to zero tension. The tension is determined by the boundary conditions. So here it's really crucial that you let the boundary conditions free. And here the boundary conditions are not at some physical boundary, they are in field space. So somehow another way to phrase these things is you have a system whose field space is compact somehow, and that compactness buys you this. Anyway, so once as you all understand now, once the tension is zero, this gradient energy is zero, and so you are dominated by higher derivative corrections, in particular
Sorry, Albert,
Yeah.
field space is compact, but the mapping should be one-to-one, right? You cannot have.
Exactly. So that's why I'm saying that you need to break space-time symmetries. And again, I don't have a general theorem.
Yeah, we have a compact scalar, then in different points in space, you can have the same value. While here, for this interpretation in terms of an object immersed in space, it should be one-to-one.
I don't know. I have these examples. I don't have a general.
But anyway, in the case of the solid before, what would be the candidate symmetry, like the one Nino was mentioning?
I don't have one there, yeah, but.
Yeah, because it works,
yeah, no,
it works even for
Right.
potatoes,
Right.
meaning
Right.
zero symmetries of the boundary.
I mean, it reminds me a little bit of the fact that like in other, shallow waterways go like omega squared is k cubed, for example. So the k cubed there also has a nice interpretation. I mean, so it's also weird, but there it's the fact that the ripples on top of the water make all of the water, because it's water's incompressible, make it all go up and down, so you get some extra you get some sort of k in the time kinetic term. So that's what turns it to omega squared. So there are other examples like that where you could say, where's the k squared piece there? But there too, there's something a little bit non-local. Water's incompressible, so as it goes up and down, you get some extra k. But yeah.
Well, also in the superfluid, when it becomes free, you get k squared. In the limit where you have a superfluid, when you turn off the quartic, you go from k to k squared, right?
Yes.
That's also related to some symmetry. Symmetry of 50 or
Yeah.
related to that. Right.
It's
The
also-
speed of sound is square root of the quartic. Right. That's.
By the way, I mean, you probably, people in the audience will remember more than I do, but wasn't there a similar surprise with the ghost condensate? Where omega squared goes like k to the fourth? But it goes like k to the fourth there sort of dynamically because of gravity, that the cosmological solution drives you towards the place where p prime, and the p of x, and p prime is 0. And then, but that's because of gravity. That's because of the back reaction on the gravity. But then somewhere around that point, the k squared term goes away.
That's true. Yeah, so I think these are all interesting examples, and in all of these you break
There's a
some
space-time
space
symmetry. Yes,
So
I understand. Right.
I think it.
More generally, what you get is a cosmological constant.
Sorry?
More generally, what you get is a cosmological
Yes, that's
constant.
right. But
So it's
assuming,
no,
yeah, right.
yeah.
Yeah,
but
that's right. At least it's the same tuning as this is.
Right.
That's right. Yeah. Right.
So it's not any,
Yeah,
you could
right.
say, whoa, in gravity, I get these maximally symmetric solutions, but so what?
Yeah.
It doesn't look as much like a tuning. Here, you seems like you really get 0 in some sense, right? It looks different.
So in the example that Ricardo mentioned in superfluid, right? So in that limit, it's just a free particle. You have a bunch of free particles. Let's say we switch off quartic, and then the dispersion relation omega equals k squared over 2m is just the fact that you are moving the existing particle.
Yeah.
So I don't know if this is similar to this in a sense. You start from a different place because you broke in the points in line.
Thank you. Okay.
Oh boy.
Everybody's we're all thinking the same thing.
I got it, yes.
Anyway, so okay, let me address for a second the question about the surface tension. So suppose, I mean, of course, once you have a boundary, you're breaking some of those internal symmetries that you have in the bulk, okay? Because the boundary happens at some finite phi. So in particular, I had this, which was constructed in terms of some internal symmetries, but now this function of phi does break them. So even if you don't put them originally, in general, you will generate boundary terms, okay? And the boundary terms usually, I mean, in biophysics, for instance, they are modeled very, in my opinion, very crudely as some sort of literal surface tension, so term proportional to the surface without any other dependence on the fields. I think more in general, one should have a boundary Lagrangian that depends on the fields in some ways, according to the symmetries. Probably by dimensional analysis, this boundary Lagrangian should be of order. I'm talking about a 4-dimensional density for now, okay? Because then the theta will reduce to 3 dimensions. But 4-dimensional energy density will probably, by dimensional analysis, have the same typical energy scales as the bulk. energy density, which is the mass, if you want for a non-relativistic solid, is the mass density times sound, speed of sound squared. And then you have a delta function with the correct Jacobian factors that makes everything invariant under, if you want, reparametrizations of this function f. And just by dimensional analysis, now you need a length scale, and this length scale will be, in general, the UV cutoff of the solid, let's say the interparticle separation of your solid is something like that, in comoving space though, because you see the delta function is, and this Jacobian are in comoving space. So if you actually check, dimensional analysis suggests that this should be a comoving UV cutoff. Plus even higher derivative correction, so delta prime, delta double prime, etc. Okay? So this is how you'd model a surface tension. And now you can just check the stress energy tensor by the boundary conditions. Now you have a new addition to the boundary equation, but there is an explicit L, which is small here, compared to, if you have a macroscopic solid, compared to the radius of your solid. So in particular, if you have many, many atoms, and you have a very large radius of curvature and then a small interparticle separation, the stress energy tensor that you get once you take into account the surface tension relaxes, not to zero, but to a small value, which is of order of the ratio of these two length scales times the energy density, the natural energy densities that you'd expect from the solid viewpoint. Okay? So if you want, from this viewpoint, the question of the hierarchy between the Tij and this small scale, this large energy density, if you want, can be rephrased as why are solids large? Why is it natural to have a stable, static configuration of an Avogadro number of atoms? Is this a relevant question? I don't know, but that's how you rephrase the hierarchy in this language. Yes?
It seems strange that if you put the solid on periodic boundary conditions, right, or you make it infinitely big,
Yeah.
then you lose this constraint that T
Yeah.
mu has to vanish, because that came from the presence of the boundary in the first place.
Yeah.
But on the other hand, if you take the limit that it gets larger and larger, this surface tension effect goes to zero.
Well, but here you're taking the limit, leaving the boundary conditions free. Whereas if you have a solid of a periodic and of a fixed extent, you are in a sense imposing the boundary condition there. Right?
Yes.
So periodic boundary conditions with, like Riccardo was saying, a mapping between, a one-to-one mapping between my comoving coordinates and the x is a boundary condition.
But then you lose this constraint that,
Yeah, so yeah, exactly.
right, so it's something that depends crucially on the existence of the boundary, but on the other hand, when the solid is very large, you don't care much about the boundary condition, about the boundary term. You don't find this strange.
So the boundary, so in a periodic solid, the periodicity boundary condition decides the tension of the solid for you. So the tension is not free to relax to zero.
Right.
If you try to force your finger into a ring that is too small for you, that ring will be in tension and there's nothing you can do about it.
I mean, maybe the statement is more that this is a boundary condition that has a sort of a physical interpretation of just being free. Because you can choose a different boundary condition and get a different answer, right? So that's, right, but it's a particular physical boundary condition that does give you this.
Yeah, because if you are deep inside the solid, you measure the pressure, you say, oh, the solid is not immersed in water, it's immersed in nothing. You know what you know something about the outside of the solid. Makes sense, right?
Yeah. If you know the equation of state.
Sure.
So if you take the same solid out of water or in water, you can tell.
Measure state, equation of state of the solid, you can measure by doing scattering experiments inside the solid. You know?
You can, but you need to know if you want the offset of the Lagrange. So when I say, sorry, something I should have said before. When I say Tij is 0 or small, I mean Tij equals the same value that you have outside the solid or small, right? So you need to know that offset.
So this is not unrelated to finding the correct maximally symmetric solution in the gravity case, right? So there's many rotationally symmetric solutions out there. It could have been immersed in water, honey. It happens to be immersed in vacuum. And when it's immersed in vacuum, you get this phenomenon.
Which is
But that's-
also, I mean, this is
yeah.
also related of why you cannot use directly this to solve the cosmological constant problem, because somehow, okay, you need an island, solid island,
Yes.
immersed in something with zero cosmological constant. So, okay, sorry, Massimo is telling me that they have very few.
Just when it got good, Massimo.
Let me just give you another example and then I'm going to close. So, a completely unrelated, apparently unrelated example is this hypothetical system, the framed. So, what's a framed? So, it's the simplest effective field theory that breaks Lorentz for the Goldstones of spontaneous breaking of Lorentz. So, if you just ask yourself, suppose I'm given a system, a condensed matter system, it breaks boosts because there is a rest frame. What is the low energy effective field theory for the Goldstones associated with that? So it so happens that it is not realistic because apparently ordinary condensed matter systems have other effective theories, but this is a consistent effective theory by itself. You just look at the Goldstones of boosts. In particular, you suppose you break boosts by the expectation value of a current or a vector operator, then you can hook up some Goldstone dressing of the VEV of that vector operator, and you write down the effective theory. You could do it also with the coset construction, get exactly the same result. So V mu here is not a fundamental vector field, it's a placeholder for this combination of Goldstones eta. Okay? And you discover that the effective theory is just a bunch of derivative terms like this, plus higher derivatives, plus a cosmological constant. And in particular, then, given this structure of the effective theory, you can derive the stress energy tensor of the theory. And again, it has a bunch of derivative terms, plus higher derivatives, which I didn't write down, plus a cosmological constant. This ground state breaks Lorentz, okay? It's delta mu 0, so it breaks Lorentz. It selects the time-like component, that's special. So on the background ground state of the system, V mu itself is a constant, so all derivative terms in the T mu nu are 0. And so you're left with the cosmological constant. So the stress energy tensor is Lorentz invariant, even though the ground state breaks Lorentz invariance. And there's no obvious selection rule enforcing that. It's a consequence of symmetries because you built the effective field theory on symmetry considerations. But there is no direct selection rule telling you that the expectation value of T mu nu should be Lorentz invariant, because Lorentz is spontaneously broken. And I see this as a somewhat a technical analog of the CC problem. Here in the CC problem, T mu nu is 0, or much more than any other particle physics scale, and there's no selection rule enforcing this. And here, T mu nu is not 0, but the Lorentz violating component of T mu nu, in particular the traceless components of T mu nu, are 0. And so, since we were puzzled, we verified this at one loop. We coupled, and just to be more accommodating, we coupled these Goldstones to a massive particle in all ways endowed by symmetries. And you compute, by the way, rho plus p is another way of looking at the Lorentz violating.
Would you mind just turning down the lights that are?
How do I do that?
I got it. Oh, I don't got it.
So when I say T mu nu is Lorentz invariant, is the same as saying rho plus p equal to 0. So density plus pressure equals 0 is the same as saying there is no Lorentz violating expectation values of T mu nu. So just look at rho plus p. If that is 0, the T mu nu is Lorentz invariant. Rho plus p happens to be, so if you take this effective theory, you couple it to a massive particle, you compute it to one loop, the expectation value of T mu nu, it happens to be a sum of 11 terms. Each term is a complicated integral like this with some coefficients, some powers, and for generic coefficients and powers, for generic powers, the result in dimensional regularization of this integral is this mess with gamma functions and hypergeometric functions. And this is the table of the 11 terms with all the different coefficients, the different exponents, and the different coefficients. And I don't know if you can see, but the different coefficients depend on some free parameters of the effective theory. One, thank you. I have the speed of sound, I have a mass parameter, I have two coupling constants, B1 and B2, that tell me how you couple to the this massive particle, and when you sum, so you see each individual term is a mass, when you sum all 11 of them with these coefficients and with these powers, you get exactly 0. So this is a case in which there is a huge cancellation of terms, totally without, or at least for me, without any obvious structure. It's not obvious where these cancellations come from, apart from the fact that you kind of knew that they had to cancel. So I have another example, but I'll conclude here. So there's explicit examples of apparent fine-tunings when you break space-time symmetries. Here I stress in nature because, again, you pick up a random rock and it's apparently tuned, according to what I told you. And I had 2 more examples, one of which I could not talk about, scalars at finite density. And I don't have any conclusion or general understanding of this. So it would be nice to see whether there's a general lesson to be learned to understand when these things happen and whether, okay, it's kind of just a curiosity or whether there are potential applications to our problems in theoretical physics. Thank you very much.
Thank you for the talk. Any question?
I mean, you must have thought about this. I mean, you can formulate gravity sort of formally as something very similar to this in the, you know, the Vierbein formalism, and it sort of looks like you're identifying, you know, in the vacuum, you're identifying the fields with the space things, you know, so very much like this. So this might suggest that somehow you try in gravity to impose some weird boundary condition that you wouldn't have thought of if you didn't have this example. Have you
You're
tried
not talking about the solids or the
No, I'm talking
fluid?
about now, I'm talking about gravity, the real cosmological constant problem.
Yeah.
So since you did this, I mean,
Yeah.
there is a kind of a formal analogy between these kinds of theories and gravity, right? And the,
Those
like,
Stuckelberg fields.
but, yeah,
Those Stuckelberg field, or because you mentioned the Vierbein, but you say the
No,
analogy.
you say that these are geometrical theories.
Yeah,
They're
these-
essentially theories of geometry.
yeah, they're geometrical theories, but I can think of these, if I just thought of these Vierbeins as some gauge fields with some internal indices, I would normally have them fluctuating around 0, but in gravity I don't. I have them fluctuating around these background solutions that are formally, you can think of them as identifying the Vierbein with the space.
Just mean E A mu is delta A mu.
Yeah,
right? That's just
exactly.
exactly.
It's
like-
exactly like this, right? And so, but now if I somehow take that picture seriously, I think of it as some sort of weird solid or something. Does
So
this?
that's why I'm saying you're talking more about the Stuckelberg parameterization, not about the Vierbein, but about some phi mu that take x mu as expectation values. Is that what
Maybe this is gonna take too long, but maybe, I think I'm just talking about the Vierbein, but maybe we should, I don't know if we want to talk about this later, but it just seems to me like gravity looks a lot like this, at least at some sufficiently formal level, so it'd be worth thinking through if you tried to make these sort of boundary conditions, what does that look like? Does it make any sense at all? Does it
That's a
just?
good question, I don't know.
Well, there were these ideas across the decades of diluting the cosmological constant.
Yeah, I mean, a lot of people have thought about
In a
this,
sense, it
that's saying
sounds-
that you can think of gravity as an SO31 gauge theory or something like
Well,
that.
imagine slightly analogously, imagine you just had two vacua separated by a domain wall. If the vacuum energies on the two sides are not the same, you're not going to find a static solution. So the wall is going to sweep through one or the other. And if you happen to be in a situation where there's a static solution, then magically the tensions on the inside and the outside have got to be the same. It sounds a little bit similar
Yeah,
to
something,
your,
exactly. Is there some, maybe there's even, some physical picture where there is an outside or a boundary or something like that.
But I think you're always going to be in the situation where you have to explain why the CC is 0 out there. And also we're going to have the problem of gravitational back reactions screwing you up. So if we have de Sitter, it's going to, inside it's going to sweep out the wall. If it's ADS, it'll crunch, blah, blah. Usual problems. But I think formally, if you want to say that you have a situation with two vacua and you happen to be in it's static or something, then that'll only be possible if the tensions are fine-tuned.
Yeah. But on the other hand, this tells you that in general you will not find a static solution.
Yes.
Whereas for solids, there's plenty of static solids, so it's not an external.
But the analogy with the axion, I think, is if I had been presented this right, if I had thought that is the first thing you would think about in terms of analogy. If there is a, yeah, I don't know. I would consider that. But by the way, Alberto, the rho plus p equals 0. Do you think that the thermodynamic argument, this is 0 because all this is not going anywhere, right? Because normally you have rho plus p equal t times entropy density plus mu times charge density, and your frame in the frame it does not have any temperature, does not have any charge. It's a featureless finite density system. And there can only be 0 by thermodynamics. But is there a way to turn that into?
I don't know. That's an interesting question. Is because at some level it's like saying there's a relationship between thermodynamics and Lorentz invariance.
If it was thermodynamics, wouldn't he'd calculate something and then you'd relax to a new minimum where rho plus p equals 0? It wouldn't just be that all loop contributions to the static system give you 0.
So in this case, there is no relaxation whatsoever. There is no landscape. There's no
doesn't seem
continuum. There's
thermodynamic.
no.
When you write rho, I mean,
There's no moduli space. There's no continuum of
E
solutions.
plus PV, thermodynamic E plus PV equals sum of all product of conjugated quantities, T and entropy, mu and charge density, strain, and if you have a solid, and the other thing I know to call it is the chemical potential in the spatial direction. And in this case, you don't have any other conserved charge than the Poincaré. You're at 0 temperature, so you cannot have anything on the right-hand side. So you get 0.
But what if I were to do thermodynamics in a non-Lorentz invariant system?
No, exactly. This is, I agree. I'm just saying that. Yeah.
Any other questions? I was very twice that the solid and what did you put in this solid? The very beginning.
Yeah, sorry. Because if you have a liquid or a general fluid, these internal symmetries that I was talking about, okay, depending on phi, get, or if you want this one, here I have some rotational symmetries, get promoted to a volume preserving diff, because a fluid is is a system in which if you, let's say, you start from the equilibrium state, and then if you deform it without compressing or dilating anywhere, you don't pay any price for fluid without. And so it's a much bigger symmetry, and in a sense, it makes the dynamics richer. But also, and in fact, it's a good question, because I have a puzzle here. I don't quite know for sure when we say, okay, gas is a system that if you let it go in the volume, it fills all the volume. So it means that something like this relaxation at 0 pressure but finite density for a gas does not exist. And it's not obvious from the effective theory viewpoint why it doesn't exist. Why can't a gas be at 0 pressure and the finite density? So there's a puzzle there which I don't know how to answer.
Thank you. Nina, IMF from Institute of Advanced Studies. You would be.
Yes. So, I have a lot of Ricardo stories, but I'm not going to share them all now. We're going to leave some of them for dinner. But I do want to say a somewhat serious thing, at least one somewhat serious thing. Probably it's true for most of us. It was certainly true for me. When I was a graduate student, sort of thinking about the kind of physicist I aspired to be. I didn't think about the big shot famous people. They all seemed infinitely old, infinitely sort of irrelevant, arrogance of youth. But I did think a lot about the sort of postdocs in the just 5, 6 years older than me, the kind of next generation up. And sorry? What? A, all right.
Maybe you're not thinking.
Anyway, I was thinking, right, well, that would have changed everything then. And there were a number of these that played an absolutely huge role in my intellectual life when I was a grad student at Berkeley. There were 4 of them who were my sort of intellectual heroes, the people that I aspired to be like. And I'll tell you who they were in order. In order, they became, they played these roles for me. The first one was Marcus, who you probably don't remember, but we actually overlapped a tiny bit.
What do you mean I don't remember?
We probably overlapped a tiny bit. The first one was Marcus. Next was Gia. And I did not meet Gia for a long time, but I started reading his insane papers, and I thought they were totally amazing. Then Raman, and last but not least was Ricardo. And I say last because I actually resisted taking Ricardo as a hero for a little while, because his papers back then were so boring that when the papers with Uri and my advisor, they were not super exciting papers, but they're okay. They're okay.
I mean, I'm not getting offended. I'm not
you're not
getting
getting offended. They're pretty boring papers. They're fairly boring papers. TP tau unification. Anyway, they're very nice papers. But actually, Ricardo became a hero very indirectly because all the people I thought were cool thought Ricardo was cool, and I thought there had to be something to it, you know. There had to be something to it. Anyway, we eventually met in person, and I'd say, I mean, all these people were incredibly important to me, but I felt spiritually the closest to Ricardo. I think we're the most similar in our outlook on the world, on physics, on other things, and we wrote some papers I'm extremely proud of together. And he's had an absolutely humongous influence on my intellectual life. We have not worked together in a while, but he's had an enormous influence on my intellectual life. So thank you for that. Another extremely important effect that he had on my intellectual life was being an extremely good judge of young physicists. And so I got, when I was at Harvard especially, a number of amazing youngsters that, you know, I just hired based on Ricardo's recommendation. A few of them are here today, like Sergey, Alberto. These people were totally awesome, and it was Ricardo who told me, you should just take these guys. They're totally awesome. So I trusted him, and he was right. As I said, I have like 1 million Ricardo stories. Maybe not 1 million, but 1,000 Ricardo stories. But I can't resist at least sharing one of them, because this actually illustrates also the sense in which I think we think very similarly about things. It's not a story that I witnessed in person, but is an anecdote I heard from Paolo Cremonelli. So Paolo apparently was taking a quantum field theory class from Ricardo at Pisa, I guess. You know the story, right, Ricardo? I don't know if you know the story.
Honestly, I don't remember.
You don't remember?
They only know.
Anyway,
So I learned it from.
We recall it every other week.
I'm sorry, we call it every other week. Anyway, for those of you who don't know the story, apparently Ricardo's explaining about the renormalization group. And he keeps going on and on about how amazing the renormalization group is, and there's no dependence on mu. Nothing depends on mu. Paolo apparently is a very, very smart guy, still nonetheless is a little confused, because he doesn't see any mu on the blackboard anywhere. There's no mu variables at all, so he doesn't even know what mu is being referred to. And so meekly, according to Paolo, he puts up his hand and he asks, what is mu? I don't see any mu anywhere. And Ricardo doesn't skip a beat and says, exactly.
It was actually me.
It was you! Anyway, it's the sort of thing I would only aspire to do if it was me doing it. So, anyway, I'll save the rest of the Ricardo stories. I'll just also to say that whatever you think about the horizon you're crossing, it's totally irrelevant. 60 is the new 40.
Yeah, the horizon.
You're fine, at least before you die.
No fire.
All right, so I only now have, what, 35 minutes maximum, if that. So I thought what I would do is just tell you a little bit about some of the work that I've been doing over the past, well, many years, but I'll try to keep it somewhat self-contained and tell you about some of the things that I've been most excited about just over the past year. So the title was Surfaceology and the Real World. The sort of foundations for this work was set in a collaboration with some wonderful young physicists and mathematicians over the course of the pandemic. where we started understanding how to think about a very simple theory, a theory of a colored scalar particle. So phi is just an n by n matrix, and we just have a trace phi cubed interaction, where we understood how to formulate this theory in one of these interesting new languages of the sort that you've been hearing me go on and on about for the past 10 or 15 years, where the basic ideas have nothing to do with Lagrangians or Feynman diagrams or path integrals or anything like that, but instead involve some very simple sort of geometric, essentially combinatorial ideas that are formulated in the kinematic space of the data that specifies the scattering process. So here we're talking mostly about scattering amplitudes, although what I'm talking about today really extends in a quite natural way to general correlation functions. I'll talk about amplitudes. Anyway, there's a picture. The words that go along with this, well, surfaceology is one word. Binary geometry is another word. I'll explain what some of these things mean. These things are adjacent to, but not the same as string theory. There's a sort of larger set of objects and ideas that there's no world sheet in sight, there's no conformal field theory, so it's certainly not the standard way of talking about string theory, but there's a sort of point in the space of these theories that we're talking about that really does turn into the bosonic string. And there's a different formulation of what the bosonic string is, a very different set of variables in the coordinates. Anyway, that was the work that occupied me starting from 2019 and then going through the pandemic. And we figured out how to do this at all loop orders beyond the planar limit, all orders on the topological expansion. But what I've been most excited about over the past year is understanding how these ideas, which I thought, you see, the reason to focus on this trace phi cube theory is it's a colored theory, okay, so it's a normal sort of colored theory, just like gluons, but it's much simpler. There's no numerators. Okay? All you have is the amplitudes are just built out of propagators. There's no non-trivial interaction, momentum-dependent interaction vertices or anything like that. So I thought of it as but the singularities of this theory, the kind of poles that you would see at tree level or even at loop level, are clearly universal. The downstairs is the same. You know, gluons, more interesting theories will have stuff upstairs, but the downstairs is the same. And obviously the poles in the singularity structure is very important. So I thought it would be a great start to understand what happens or reformulate our understanding of this very, very simple theory. And then after we did that, we'd have to start all over again and figure out how to incorporate polarization vectors and momenta and more complicated Lagrangians. Then it'll be another sort of 5 years before we figured out how to do all of that. And the big shock for me, and the reason I'm so excited, is that it turned out to be vastly simpler than that. And this theory actually secretly contains many other theories that we care about. So it's not a matter of changing it, it's simply a matter of reinterpreting exactly what this theory is. Again, a fact that's not a slogan, but it's sort of very literally true. And I'll try to explain something about this, the self-contained parts, is that these three theories, the trace phi cube theory, the nonlinear sigma model, and Yang-Mills theory, non-supersymmetric Yang-Mills theory, are in fact secretly the same. And when I say secretly the same, it's not that secretly, well, somewhat secretly, but there's one and the same function. There's a single function that you can call what we call the quote-unquote stringy scattering amplitude for the trace phi cube theory. And simply reinterpreting what you mean by the kinematic variables of that function, just expanding around to different kinematic points for the single function gives you either the nonlinear sigma model or Yang-Mills theory at low energies. And the conjecture is that it's true at all loop orders, all orders on the topological expansion. Some of this conjecture has actually been proven. And in particular, this connection is easiest to describe, and that's what I'm going to focus on in the remainder of my time today, because it's very simple to talk about, and it's already quite striking, and it gives you some idea of what is going on.
So Dima, in the phi cube theory,
Yes.
the high order and perturbation theories know about the fact that the theory, when it does not have a real vacuum state.
We don't see any of that in perturbation theory. You see all the things about vacuum
the
instability.
behavior,
Yes.
the structure of the series
Yes.
somehow encodes that if you.
No, it's not the structure of the series. It's not, I mean,
Well, if you say
like-
it's not Borel summable, there are Borel poles in the Borel plane, stuff like that, and just.
so there is stuff like that. Of course, that's not super specific to the trace phi cube structure.
Yeah,
It also
no,
be there
I-
for trace phi to the 4. No, I mean where that shows up is in. I mean, it's true. Non-perturbatively, the vacuum amplitudes have imaginary parts. Okay, but it's a non-perturbative thing. So here we're just focusing on what you can see in perturbation.
And what do you mean exactly by nonlinear sigma model? I mean,
There's many of them. I will tell you.
of counter terms.
Yes, right. So first of all, so it turns out that there is a very specific sigma model. So you know, there's our favorite chiral Lagrangian sigma model. There's another one. So these are just what the cosets are, okay? And so, first of all, the shift that we're talking about, first of all, at low energies gives you amplitudes that turn out to be those for this coset, okay? K doesn't matter, it turns out. So, in this entire business, when we talk about amplitudes, we're stripping off kind of trivial dependence on coupling constants and things like that. So the dependence on N and K is trivial here.
So I'm asking about
Yes,
terms.
that's right. But then, so what we're really talking about, first, the low energy, the two derivative structure is universal, is just controlled by the coset. But more specifically, we get a particular funny UV completion of these of this NLSM. So this shift is giving you a very particular strange UV completion, but still a UV completion of the NLSM. It turns out to be this NLSM. We didn't realize it for a little while, but it's this NLSM. But this guy and that guy, interestingly, turn out to give identical amplitudes to all orders in the planar limit. Okay, so at tree level and to all orders in the planar expansion, they turn out to be identical. Okay. But in general, it's a specific UV completion of these guys. And maybe in going with the in keeping with the theme that we had from Alberto, it's not just that we get some sort of abstract formulation of these theories in different language, but this different way of thinking about things makes obvious certain facts about the amplitudes that we did not know before. Okay? And I think this, to me, is the most exciting and kind of striking thing going on here. Because these are ancient objects that we have known for a long, long, long time, and there are totally new things about them that we did not know until this year. Okay? So, in particular, there's a very general phenomenon of what you can call a split factorization. There are many things I could be talking about, but I want to just talk about this one because it's both very simple and it goes also with the theme of what Alberto was talking about, ultimately sort of features of physical systems that don't have obvious symmetry explanations, but are nonetheless true. Okay? We're very familiar with, just at tree level, that amplitudes have important properties, like they have poles, and on the poles they factorize into the product of lower amplitudes. So the usual most important sort of analytic feature of amplitudes are their poles, and we know that on the poles they're supposed to factorize. This is a different phenomenon. Oh, I'll just come. Yes, go ahead. Yeah.
How many dimensions are we?
Any number of dimensions. Any number of dimensions. So that's one of the important points. It's a dimension agnostic way of thinking about things. So this is the sort of usual story that we have factorization of amplitudes near poles. This is that there's some locus in kinematic space. So something that actually just involves setting a bunch of dot products of momenta to zero at tree level. There's loop level extensions, but I won't talk about them here. These statements extend in an interesting way to all loop orders. But there's some particular set of pi.pj's that you set to zero. And on this locus, no poles, nothing's going on, but on this locus, the amplitudes factorize into the product of, you have some n1 times n2. No poles. So that's a very interesting phenomenon. that everything is smooth, but you set a bunch of kinematic invariance to 0 and the amplitude factorizes, so the product of lower point amplitudes. This has a consequence that the amplitudes have zeros. They have zeros when you just arrange it so that one of these simple factors is a 0. Okay, so the amplitude has a 0. And so this is an infinite series of hidden zeros that amplitudes have. Now, if I tell you about the trace phi cube theory, there's no reason it should have any zeros. There's no, it's not a Goldstone, there's nothing, right? It's just a totally boring, stupid theory. But this boring, stupid theory has a huge number of interesting zeros in it. Because of this connection, these zeros imply zeros for the nonlinear sigma model, and zeros for gluons as well. Okay, in fact, I'm telling you this story backwards. My partner in crime is here, Carolina. We've been working together on this stuff for the past year and a half or so. And she can attest that the story was totally backwards because we discovered the zeros first, and then saw that the zeros were shared by the nonlinear sigma model and by Yang-Mills theory, and then tore our hair out, well, mine is almost all out already, to try to understand where the hell these zeros were coming from, why it was the same for all these theories, until we realized that all the theories were actually the same. Okay, so that was that was the historical genesis of these ideas.
Just for the
yes.
clarification,
Yes.
perturbatively, we know Yang-Mills is asymptotically free, at least in
Yes.
C.
Yes.
So that one is also,
Sorry?
so the other ones are also asymptotic free?
No, well, the connection to asymptotic freedom, et cetera, is after you do loop integration. Okay, so these are all also true post loop integration, but I think that this will make the connection to the NLSM is not UV free, right? The NLSM breaks down the UV, and so this trace phi cube you should really think of as some UV completion of the NLSM. Okay, and if I have time, I'll even tell you, give a simple Lagrangian understanding of what that connection is. I'm not sure how.
Conversely,
The connection to Yang-Mills is a little bit, that's why I'm not talking about it here. The connection to Yang-Mills goes to the sort of stringy version of this trace phi cube theory, okay? So the stringy is in quotes. It's what I mentioned before, but anyway, the kind of stringy version of the trace phi cube theory. There, the shift of kinematics that you do is order 1 in string units. So it's very hard to sort of think about what that shift means, sort of purely from the low energy field theory point of view. So that's where all the kind of things that you're talking about, the differences come in. Okay? But it's still true that there's one function. You literally expand the function around different points, and you get phi cubed, NLSM, or
but by the way, the phi cube in 6D,
Yes.
this Ahmed asked, that's asymptotically free.
yes, phi cube
But
is that's
this
right.
as well with matrix.
But
Oh,
also
sorry,
three.
no, that's
Also
right.
4.
Yeah,
Also
but-
4.
Yeah, no, I mean
Soft.
Yeah, it's soft.
Classical
That's right.
asymptotic.
That's right. Yeah. No, but this whole thing is dimension agnostic. Okay, so whatever the theories do, they all right. Okay, so this is so I'm going to try to explain mostly. I'll say a little bit about what this story looks like, and then give you a flavor for what this connection looks like. But actually write down some concrete formulas so you can actually see. Ah, sorry, but I forgot to say. So I said that there's no reason for the trace phi cube theory to have zeros, but it has zeros. So those are zeros that we can't explain by symmetries. And there's a whole pattern of them. Now, when we shift to get the nonlinear sigma model, you might think, well, surely what are these zeros? The nonlinear sigma model is supposed to have zeros. It's the Adler zero. It's a thing that's guaranteed by asymmetries. And that's not these zeros. These zeros are actually more general than the Adler zero. They imply the Adler zero, but not the other way around. So that's what's so striking about this. Maybe no one cared about the trace phi cube theory, so no one studied it to see it had zeros. The NLSM has been studied to death for 60 years, and I'm telling you, it has bigger zeros than the Adler zero. Those zeros have no symmetry explanation that we know of. They imply the Adler zero, but they're not a consequence of the Adler zero at all. So that should give you some idea why we care about these things, is that there are sort of facts about this object that all of us in this room know and love that are new.
So these are specific zeros at points where some
Yes,
J
exactly.
on the stone leg are
I'll
zero.
explain
It's
exactly
not
what this
other
looks like.
kinematic, it's
No,
those specific.
it's some quite specific kinematic points, but these kinematic points are a little bit more general than soft limits. If you further specialize them, you get soft limits, and that's where the Adler zero comes from. But they're actually more general configurations. Really, they descend from this. really, conceptually, they descend from this sort of kind of remarkable fact that there are loci in kinematic space away from poles where the amplitudes factorize. Okay? Whereas normal zeros are close to factorization. Why is there an Adler zero normally? You know, what soft theorems? Where do the soft theorems come from? Soft theorems come from the fact that you're emitting a soft particle. So the only place that could possibly have a singularity is collinear limits. And then if it just so happens in the case of the signal model that you go from an even point amplitude to an odd point amplitude where one guy goes soft, it has to be zero, right? So it's closely related to poles. So the usual, in other words, even the usual story of zeros, of course we also give them symmetry explanations, but the mechanical explanation for them from the way Adler got it before knowing about the nonlinear realization argument is to understand them as essentially following from factorization. There's just a new kind of thing. It has nothing to do with what's going on near a poles, which explains the origin of these zeros and many, many more things. Okay? So what I'm going to try to do in the time I have left, and how much is the time I have left? You're not even paying attention, man. Come on. If you're going to, oh, you are paying attention.
Pay attention to the time.
Oh, to the time. Good, good. Well, then you can tell me how much time I have left.
14 minutes and 30 seconds.
Oh, that's very All right, so let me just try to give you a flavor for what these, what this shift is. All right, so well, maybe I'll actually jump. Maybe I'll jump to the end and can tell you what this. I'll tell you what this connection is because I have 14 minutes. Actually, if I have 15 minutes. I think I won't say too much about this story because I want to tell you something real. I want to show you something. So let's just talk about what this connection actually looks like, even just at the tree level. To begin with, let me just talk about the kinematic variables for the trace phi cube theory. And so if we use the usual double line notation to describe what the fields look like and what the interactions look like, then we draw these kind of diagrams. For example, at 4 points, I have the S channel and the T channel, but no U channel. If I'm talking about color ordered, if I just talk about color ordered amplitudes. Okay, so. And here, the 1, 2, 3, 4 are referring to the color indices. So this is color index 1, color index 2, color index 3, color index 4, and so on. Just usual picture of a color order. All right, so you see in this 4-point interaction, the S channel, I'm ignoring the coupling constants, is 1 over P1 plus P2 squared. The T channel is 1 over P2 plus P3 squared. And so you see the objects that show up in the propagators are sums of consecutive momenta. Okay, so that's what the color ordering buys. And so there's a sort of a, by now I think, very well-known picture. Again, because the particles are naturally ordered, we can imagine putting the momenta end to end to form a closed polygon. So this would be P1, P2, P3. And so the fact that we have momentum conservation just tells me that the polygon is closed, so I can think of each PA as some difference between the coordinates, the vertices of the polygon. And then there's a very natural set of variables, just in Lorentz invariants, that are just the distance squared between 2 points on this polygon. We can call those xij, which are pi plus dot dot pj minus 1 squared. And these are these happen to be, of course, these are the propagators of tree diagrams. But they're also, quite beautifully, a basis for all possible Mandelstam invariants that we can have in the problem. So since we're talking about scalar amplitudes, they can only depend on the pi dot pj. So we could just say, why don't I just use the pi dot pj as a set of invariants, but the pi dot pj satisfy constraints because of momentum conservation. So if I take the sum over j of pi dot pj, that's equal to 0, so they're not all independent of each other. And this is a pain. So you can, for example, choose a solve for the nth momentum in terms of the negative, the sum of the rest of them, but that breaks the symmetry of the problem. So the actual number of Mandelstam invariants is n choose 2, which is the number of pi dot pj, but minus n constraints from momentum conservation. And you notice that this number is exactly the same as the number of chords of this polygon. Okay, so the xij are in fact a nice independent basis for kinematics. That's very, very important. Okay? If I specify just a collection of xij, a collection of numbers associated with the chords of a polygon, I'm done. I've specified some legal set of kinematic data. At least if I ignore the constraints of living in a fixed number of dimensions. So here we're imagining the number of dimensions as large as we want, so there's no constraints of the form that say, if you have 5 vectors in a 4-dimensional space, they have a linear dependence with between each other. So they're called grand determinant conditions. We're ignoring grand determinant conditions. And that's fine because the amplitudes don't know about them. The amplitudes are only a function of the Mandelstam invariance. And so if you give me the amplitude for a phi cube theory in 3 dimensions, you know it in 100 dimensions. Okay, it's exactly just a function of these kinematic variables. Okay, so in terms of these variables then, let me write down a few amplitudes for the trace phi cube theory. So for instance, if I'm at 4 points, so we just said it's a 1 over s plus 1 over t, but if I draw what s and t look like in this polygon, that would be 1 over s, right? And this would be 1 over t. And you'll notice, not coincidentally, that here I've just written what the propagator looks like, but I can interpret this picture as a triangulation of the square. Okay? And Feynman diagrams are in fact nothing other than correspond to triangulations of these n-gons. And you can read off the Feynman diagram by just drawing the dual diagram to this picture. You just put a point in the middle, usual way you draw dual diagrams. And so a triangulation is the same as a Feynman diagram. So if I was at 5 points, I would draw a pentagon. This would correspond to one Feynman diagram. You would again draw the dual diagram like this, and you'd add its cyclic cousins, and that would be the 5 terms for the 5-point amplitude at tree level. Nothing deep going on here. Okay, so to get the trace phi cubed amplitudes then, all you have to do is the official Feynman diagram definition is the sum over all the at tree level, the sum over all the triangulations of the polygon and the product of the 1 over x's for all of the x's in the triangulation. Okay? And so for every, so here I'd have 1 over x13, 1 over x13, 1 over x14 corresponds to these 2 propagators, and I just do that for all of them. Now, what we figured out in the pandemic, blah, 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 is that there's a totally different way of formulating what this is as a different object, combinatorics, blah, 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 but I'm not going to need that for the remaining 8 minutes. So this is a perfectly simple way of getting trace phi cubed amplitudes at the tree level. Now, here's the claim, is that to get from here to pion amplitudes at tree level, and I'll tell you what to do to get it at a loop order. Well, maybe I'll just tell you what to do to get it at tree level.
So
yes.
the property of factorization you were saying before,
Yes.
does it become evident?
No, this is just Feynman diagrams.
Yeah,
it's
yeah,
totally
exactly.
unobvious.
Is
That's
there
right.
any way?
Yes, yeah, I'm going to tell you. I'll tell you in a second what this interesting locus is, but let me first tell you what the connection is to the signal model. Okay? So the claim is that to get the NLSM amplitudes, first of all, the NLSM amplitudes only exists for an even number of pions. Okay? So that means I start with the trace phi cubed amplitude for an even number of phi's on the outside. This is going to be a function of the x's. That's a kinematic data, so it's a function of these x's. But it's given by the trace phi cubed amplitude, where what you do is the following crazy thing. You take the x's where the 2 indices, the ij indices, where they're both even, and you shift them. Even plus delta. The ones where they're both odd, you shift with a minus delta. And the ones where one is even and one is odd, you leave alone. There's supposed to be an exclamation mark there because this is not supposed to be obvious. Okay? Now, let me just tell you how practical this is. Because it's trivial to calculate these amplitudes, even without any work, even without any fancy schmancy stuff. We have fancy schmancy stuff too, but it's really trivial to get these at tree level in 100 ways. You take them, you shift like this, and then all of a sudden you have NLSM amplitudes. And the NLSM could not look further away from trace phi cube theory. It has even point interactions only. It has infinitely many interactions. It has this fancy nonlinear realized symmetry. Trace phi cube has none of them, but this is the relation between them. To literally get the NLSM, I'm going to go to low energies compared to the scale delta. So I'm going to imagine that this x is much, much smaller than the delta. Okay? So if I work for x is much, much smaller than delta, then I get the NLSM at leading order, and then I get an infinite tower of correction. So that's the sense in which this is a specific UV completion of the NLSM.
And is it unitary, this completion?
It's unitary, but it has tachyons. Okay, so that as you can beautifully see here. Okay, so some particles have positive mass squared, some particles have negative mass squared. So it's a funny UV completion, but just to make this point, we're certainly allowed in effective field theory to talk about low energies compared to tachyon masses. It makes perfect sense. You can get totally reasonable theories. Where the famous instability associated with tachyons would come in is if you did loop integration. If you do loop integration, now you're going to hit cuts, even for vacuum diagrams, where the tachyons go on shell, and that's where you're dead. However, nothing tells me even that this delta has got to be real. If this delta is real, then I'll have a theory which is unitary but has tachyons. And make the delta imaginary, I have a theory which is perfectly okay, but of course is not unitary in the UV. So you should think about these as sort of funny UV completions of the
this is a non-unitary UV completion.
Either you make delta imaginary, it's not unitary, or you make a...
It's like the mass of the row, only that you do it without vector, without the standard sigma mode of the...
Yeah, that's right. So
this is another UV completion.
This is a different UV completion, and in fact, now let me tell you, okay, so let me tell you two things in the 5 minutes that I have left, but this, since Ricardo is so smart, I'm going to try to squeeze both of these things in. So let me first explain. First, so let me at least make the following statement. So this is just a claim. Again, all of this follows quite trivially, and the paper that I just put out last week with Carolina, I think is the clearest conceptual explanation for where this comes from this story. It's really a one-line explanation. We somehow managed to write a 50-page paper for something that has a one-line explanation. But anyway, you should just read the introduction of this paper.
I think we should go back to the old days when the papers were 3 pages.
Yes, I agree.
Isn't there a way to decide to do that?
You're the boss here today, Ricardo. You can make us all promise.
I just want the paper of 100 pages on flavor, so I don't.
On flavor, well, that's that's even worse.
Yeah,
I mean,
no, that's what I'm saying.
Yes.
Good.
Okay, so let me explain what this picture is for a second. So what I'm doing in this little picture is just recording all the chords of my polygon, right? So notice there's 1, 3, 1, 4, 1, 5, 1, 6. You take every chord. In this case, it's a 7-gon. I have to draw a 7-gon in real time. 1, 2, 3, 4, 5, 6, 7. There we go. Okay. So I have 1, 2, 3, 4, 5, 6, 7. And I take every chord, 1, 3, 1, 4, 1, 5. So I'm just arranging them in the most obvious way. Okay. For some reason, I've chosen to tilt the whole picture by 45 degrees, but apart from that, it's just the dumbest, most obvious way of recording all the indices. Now the picture goes on forever, right? Just by cyclic symmetry. But notice that 1, 4 and 4, 1 are the same chord. 3, 7 and 7, 3 are the same chord. So if you want to just choose one copy of all of the chords, you've got to make some choice. Okay, so this little right triangle is one of the simplest choices that you can make that sort of captures all the variables once and only once. Okay? Now, these pictures have a lot of beautiful things about them, but one thing that they help us do is sort of visualize what these patterns are that I told you, these funny pi.pjs. I told you that if you set a pattern of pi.pjs to 0, the amplitude either has a 0 or it factorizes. More generally, it factorizes. And that pattern, for very good reasons that I don't have time to explain, is associated with what looks like causal diamonds in this picture thought of as a space-time. Okay? So this is not ordinary space-time. This is some crazy auxiliary 1 plus 1 dimensional space of just indices, nothing else, right? The 2 here is that the chords have 2 endpoints. So there's nothing physical about this 1 plus 1 dimensional space. Nonetheless, there's a lot of senses in which you should think of this direction as time and this direction as space that I don't have time to get into. But in any case, what you're supposed to do is take a causal diamond that's anchored to these boundaries here. So these are boundaries because this is 1, 2, 2, 3, 3, 4. These are the kind of external guys that don't have any variables associated with them. They're p squared or equal to 0. So you take any causal diamond in this picture, you just shoot out 45-degree lines like this. Okay, so that sort of lights up a rectangle inside this kinematic space. And the claim is that if you just read off, so every little square here has a bottom corner. So this little square has bottom corner 1, 4. This little square has bottom corner 2, 5. And the first claim is that if you just set all of those Mandelsams at 0, p1.p4, p1.p5, p2.p5, all the Mandelsams to 0, in this picture you get a 0. The amplitude is 0. Okay? More generally, if you leave one of them, so I'll draw the picture slightly more abstractly. More generally, if you leave, so if you turn all of them off in here, you get 0. If you turn one of them back on, so this one is non-zero, but all the rest of the guys inside are 0, then the amplitude factorizes into the product of 2 factors. And the 2 factors are associated with this upper guy and this lower guy. Okay? But again, there's no poles going on here, right? This is just some interesting factorization. It's pretty high codimension. You've got to set a lot of Mandelsams to 0. But when you set these Mandelsams to 0, the amplitude smoothly factorizes. Now, why is this related to soft limits? There's a very special case of this, which is this, what we call the skinny rectangle, which is where you just set all of these guys to 0. So this is like setting p1.p3 up to p1.pn minus 1. Okay, so if you set all of those to 0, you get a 0. That's almost the same as a soft limit where just p1 goes to 0, except literally setting p1 to 0 also would put p1.p2 to 0 and p1.pn to 0. So that's more. Okay, so to get the soft limit, you also have to set these things to 0 because you're just setting p1 to 0. The claim is that already when you just set these things to 0, that's already enough to get a 0. And so, of course, you get a 0 if you further set these guys to 0. Why don't we have zeros for the trace phi cubed? Because the trace phi cubed itself happens to have collinear poles. When p1.p2 goes to 0, p1.pn goes to 0. So it's a 0 over 0. You don't actually get a 0 out of it. However, the NLSM precisely, those shifts that we did got rid of the collinear poles, and so we get a 0. So this is the kind of simplest example where you see that there is something bigger than the famous Adler 0. And that's just a skinny rectangle. All the rectangles here are associated with an interesting pattern of zeros. Okay, so that's the first comment. And the last comment, and then I'll stop, that motivates this connection, is that you can now ask, is it possible to shift the kinematic variables in some way? Can I shift these x's in some way that preserves all of these interesting zeros, right? Preserving all these interesting zeros is tantamount, since every 0 corresponds to setting some collection of pi.pj to 0, where crucially these ij are not adjacent. Okay, so that's what we just saw. They don't correspond. See, p1.p2 is a pole that we see in the planar amplitude, but not p1.p3, not the rest of them. Okay? So there's some collection of pi.pj's that we can set to a 0. So you can now ask, is there some way of shifting the x's? Can I shift the x's in some way to xij plus delta ij in such a way that all the pi.pj non-adjacent are preserved? Now, what do I mean by this? Remember, the x's are a basis. The x's are a basis, so I can write pi.pj in terms of these x's. There's a very simple formula for it I won't write down, but it's got 4 terms. There's an x plus an x minus an x minus an x. Very simple formula that just expresses the pi.pj in terms of the xij's. So it's kind of a natural question. Is there a way of shifting the x's to preserve all of these guys? And the answer is unique. There's a unique shift which does it, and it's exactly this one. This strange one where I shift the even guys and the odd guys by equal and opposite amounts. So this is a very weird seeming shift, but it's the unique shift that has the property of preserving all these zeros. And when you understand more about this whole binary geometry world, this shift has lots of very canonical things about it. Finally, in just 30 seconds before Massimo kills me, let me just say there is a very simple, once you know what you're looking for, there's a simple Lagrangian explanation for this connection between the, well, it's a two-step, it's not, I'll give you the first step of the two-step explanation. Normally, we think about the NLSM as coming from a Mexican half potential, right? So we normally think about it as coming from some trace sigma dagger sigma plus trace sigma dagger sigma squared, let's say, where this guy is negative and that guy is positive. But there's an even simpler way that you could arrange to get a spontaneous symmetry breaking pattern. So let's say you start with an n by n matrix, I'll call it psi, and I'm going to write down the general cubic potential for it, V of psi. So it's going to have a trace psi cubed, it's going to have some mass squared, and crucially it's going to have a constant term, a linear term. Okay? Now, take this guy and look at its critical points. What do its critical points look like? Well, they have to solve the quadratic equation. I can diagonalize psi, so the eigenvalues have to solve the quadratic equation. And well, it's obvious what it looks like. The eigenvalues see a potential, which is that cubic potential. And so there's just the two, and I have something that looks like that. Right? So all the eigenvalues see this potential, but there's two minima. There's two extrema, sorry. Let's call this R minus and R plus. So if I take this psi and I make k of the eigenvalues R minus and n minus k of them R plus, so this is R minus, blah, blah, R minus, and the rest is R plus and R plus, this is k and n minus k, then this spontaneously breaks un to un minus k cross uk. And if I decompose psi as some phi, phi tilde, chi, chi dagger, then the chi's are the Goldstones. Okay? So if you expand around this extremum, of course there's tachyons, but I don't care. If I expand around this extremum, I have a theory that has Goldstones and these heavy Higgses. Now we're very familiar with the fact for the ordinary Mexican hat story that after you expand around the symmetry breaking minimum, there's relations between the cubic, quartic, and quadratic terms. The analog for that here is that there's a relation between the quadratic terms. And the relation is that the mass squared for phi is exactly equal and opposite to the mass squared for phi tilde. Okay? You can actually see this from the bottom up as the unique way of nonlinearly realizing the full UN symmetry on these fields, is you have to have this interesting relation. And that's exactly the funny relation that I showed you. That when we're doing the shift on the trace phi cubed, some things are going with the plus delta and some things are going with the minus delta. So this is the underlying sort of cubic theory which gives rise to the sigma model. The extra piece of magic I don't have time to explain, but it's absolutely intimately connected to the fact that we're dealing with a surface, the two-ness of the surface, the fact that we're talking about curves on surfaces. But that basic two-ness, the two-dimensionality, and the fact that we're dealing with curves that have two endpoints, the constant occurrence of the number 2 dovetails with the fact that we have two factors here, un minus k cross uk, and that allows this funny cubic Lagrangian with all these fields to actually be realized by kinematically shifting the trace phi cube theory. Okay, so it's a beautiful fact about double line notation and a little bit of topology that makes this fact obvious. So this is a Lagrangian derivation of this connection between the trace phi cube theory and this guy. But this Lagrangian derivation doesn't tell you anything about these funny zeros and all this stuff. That is all inherited from the trace phi cube theory. It's a trace phi cube theory that has these magical properties, which you can then kinematically shift to learn things about the NLSM that we didn't know before. So echoing again something Alberto said, I think it's a fascinating challenge. I haven't had time to explain it, but these things extend to all loop orders. If you want to see the sort of conceptual origin for where all these things come from and how it's related to this whole combinatorial geometry story, you should look at the paper we put out last week with Carolina. So there is a very simple origin for where these things come from, but none of them have conventional Lagrangian explanations. Okay? So we do not understand where these zeros, factorization, splits, any of this comes from. They're falling out of bed from this other perspective. They're totally obvious from this other perspective. They're not obvious from the Lagrangian perspective. And I think it's fascinating. They're related to zeros. They're related to better behavior in the ultraviolet than you would naively expect. There are directions you go off in the ultraviolet where the amplitudes vanish. These zeros, again, are totally unexplained. Individual Feynman diagrams blow up, but here they all magically sum up to give you zero. There's a lot of words here that are tantalizingly close to the words we'd like to say about the hierarchy problem or the cosmology-Johnson problem. And David is sitting there and will complain that I've been saying this for 5 years or 10 years, but okay, every time it's getting a little closer, asshole. So you can like, just like buzz off. Right? Anyway, thank you very much. Send in all affection, of course.
Time for a few questions before refreshment, right?
Yeah, I think refreshment is probably always the same. I don't know.
It's a little colder, but it's the same.
Oh, yeah, we are a bit like disorganized in the usual. Sergey and I, they're well organized.
Questions? Here you have a very
He was
simple-
paying attention, you see.
He was paying attention, I know.
Can multitask. The formulas for the integrants are very simple. Is the formula for the integral also simple? I mean, more
Well, I
simple
mean,
than
so the story of what in these papers from September were called this curve integral picture for where these things come from. That's true to all loop order and post-loop integration. The reason it's post-loop integration is that the entire story you should think of as giving you a canonical way of doing global Schwinger parameterization, sort of combining all you know how to Schwinger parameterize one diagram at a time, but this naturally gives you something that does a Schwinger parameterization for all the diagrams at once. Okay? But the dependence on the loop momenta and so on is automatically in Schwinger parametric form, so you can do the loop integrals as we do in the textbooks. They're all Gaussian. When you do it one diagram at a time, when you do loop integrals, you got things that are called semantic polynomials, and here you get some global version of the semantic polynomials. We call them surface semantic polynomials. It's, again, sum all the diagrams together in a single object. But then you're left with something you can literally take that, I mean, people are writing code to do it. You take the kinematic data, you hit enter, and you get a numerical answer for the actual amplitude, post-loop integration and everything. Okay? There's some fine print to that, usual fine print having to do with thresholds and I epsilons and so on, but if you're in some sort of simple Euclidean region, it's literally a matter of hitting return and it's automatic. So because of that, and especially because the NLSM needs a UV completion anyway, of course you could do it in dim-reg, but it needs some UV completion anyway, well you just do that. You take this theory, you do the delta shift, you make the deltas imaginary, equal and opposite, and imaginary just so you don't hit any of these stupid poles that we're talking about. We don't care about the fact that it's not unitary in the UV, just like we don't care about the fact that dim-rag or polygalars isn't unitary in the UV. And then that's it. Exactly the same formulae give you integrated expressions for the NLSM. So it's really practical. It's really actually practical.
The measure of integration is,
Yes.
is the same, it's in P.
It's exactly the same, exactly the
there is
same.
no
That's right.
smart
No,
going.
there's nothing smart going. Yes, that's right, yeah. And this shift is literally the same for Yang-Mills. It's just that here, I described everything in a field theory limit, but this trace phi cube theory has an enrichment also at all loop orders with something that has an alpha prime in it, okay? So if you make this shift delta and you keep delta much smaller than alpha prime, or 1 over alpha prime, then everything is happening in the field theory limit. But if you make this delta equal to 1 over alpha prime, literally 1, then you get gluons at low energies. And that's a quite non-trivial fact. And you have to ask me where are the polarization vectors. You have to ask me a lot of things, and I have to answer a few things. But there's a sort of scalar way of thinking about gluons, basically imagining a single gluon is coming from fusing pairs of scalars. And so in this way, you can talk about gluons even in a scalar language. But what's remarkable is that exactly the same shift just extends away. So you can really think that there's some amplitude. You can call it any one of these series. But let's say trace phi cube theory. When the deformation is 0, you get trace phi cube at low energies. When the deformation is generic, you get the nonlinear sigma model at low energies. When the deformation hits 1, you get gluons at low energies. Now I can ask what happens when the deformation is somewhere between 1 and 2. It's again the nonlinear sigma model at low energies. When the deformation hits 2, you get a funny theory at low energies, which is gluons plus a colored massless spin 2 particle, and so on. Okay? Now we don't expect those theories for higher delta to make physical sense. There's all sorts of theorems, as well as I do, for why these theories don't make sense.
But we still think it's interesting to explore them because this structure is not garbage. This is a very rigid, remarkable structure. So my guess is that these theories will mean something, have some purpose in life, even if they don't make standard physical sense. And these zeros and factorizations are there for gluons as well. So I can very quickly tell you that if you take that picture, I was telling you, draw a rectangle and you see all this pattern pi dot pj is 0. Here's how you get zeros for gluon amplitudes. You see, you have some pi dot pj is 0, but if you have gluons, you also have to say something about polarization vectors, clearly. So whatever pattern you thought you had, where you set a bunch of pi dot pj to 0, well, just further set the pi dot epsilon j, pj dot epsilon I, and epsilon dot epsilon j to 0. So set all of these to 0. It's the most natural thing that you could do that involves the polarization vectors. Notice that this choice is gauge invariant on the support of putting the pi dot pj to 0, so this is a perfectly sensible gauge invariant thing to do. And the claim is that if you do this on the Yang-Mills amplitude, you get a 0. Exactly the same pattern of what you did for a trace phi cube gets enriched like this. So in any number of dimensions. So that's so these are all facts about the NLSM and Yang-Mills that are very hidden from the Lagrangian as far as we know.
Thank you. So we can continue maybe discussion over donuts and cold coffee.
If you look at the theory, yes, so this theory will have a mass scale which plays a role. Which is what control. No, phi is m over g. So you have n that controls the derivative expansion, and g over m that controls the field expansion. Yes. So it's like phi. So it's a specific. You do it at the level, you get a specific. Yes, that's right. And so this is a specific. Yes, it's a specific incarnation of the low energy sigma, of the nonlinear sigma model. Other incarnations will have different. Let's say the order by order expansion.
Oh, yes, I can imagine. Yes, that's right. Yes.
Okay, so we are ready to continue with Anson Holt. We'll talk about the dynamical explanation of dark matter's invariant coincidence.
Yeah. Okay, everyone. So, unfortunately, I think my stories of Ricardo are a lot more limited than some of my colleagues here. So, let me tell you the story at least of, so the context is, at least I don't know about a lot of you guys, but at least I heard about Ricardo's reputation before actually meeting him. In particular, I heard that he would destroy speakers and like everyone was super, super scared of him. And then when I first met him, he was the nicest guy ever. And so I was very, very confused. And so the event that led me to my current sort of my theory of Ricardo right now is actually a KITP. And so at KITP, everyone, you stay there, it's a great place. They have a ping pong table in the basement. And so one day, a lot of the postdocs and I just sort of go down there, and then we see the whiteboard there, and it has a scoreboard. And Ricardo and Raman and both of their children were all playing ping pong together, and they had a huge board where they just marked down all of their scores. And it was like, Ricardo and Raman each had like 15 or 20 points, and all of their children had 0. Absolutely 0. So this is the only example I've ever seen of Ricardo possibly deserving his reputation of scaring people. And so my current working hypothesis is that if you haven't grown up yet, then you'll find Ricardo very scary, and he'll beat you up. But as soon as you graduate from that, then you'll be perfectly fine. And the only reason why this reputation has gotten into the physics sort of rumor mill is because not all physicists have grown up. A lot of physicists are still at the mental age of teenagers. Okay.
At least according to Ricardo.
Yeah.
Now I'm an old man.
Yes. Okay. So I don't know how everyone else's theory on this, but at least that's my current hypothesis. And I hope to see eventually some other data points to see and test this theory. All right. So yeah, okay. So in the rest of the time, I'm just going to talk briefly about the sort of dark matter baryon coincidence. So basically, and I assume people have heard a lot about this before, it's basically just the statement that if you look at the total energy of the universe right now, look at how much of it is in dark matter, how much of it is in the standard model, how much of it is in the CC, sort of ignore any people who tell you there's negative energy around right now. And you notice that there are about 5 times more dark matter than the standard model, and you should be extremely surprised when you first see this. The reason is back in the olden days, people were really concerned about why the proton mass is much lighter than the Planck scale, right? 18 orders of magnitude, that's a huge dimensional analysis. And eventually we discovered the reason for this was dimensional transmutation. Namely, the proton mass and the Planck scale are related by the exponential of some order 1 numbers that turned out to be something like -18. And so this is basically, of course, just the statement that, well, it's really, really easy to get proton masses 10 to the minus 20, 10 to the minus 30, 10 to the minus 40, 10 to the minus 10 times the Planck scale, right? It's very easy to change the proton mass. Unfortunately, the energy density in baryons is proportional to the proton mass, and that means this baryon energy density is also exponentially sensitive to order 1 parameters, and so the fact that it's a factor of 5 within anything should be extremely surprising. Right, so this is just why I think this is an often overlooked issue, and it should be important to at least have an idea of what could possibly explain it. And basically there's one type of solution on the market right now. It's basically just saying, well, 2 things are about the same, both of them are mass times number densities, so you just say, do a 2-step process, say the number density and the baryons and dark matter are about the same, and then you say, well, the masses are also about the same, and that's that, right? So this one type of solution, people have gone through lots of different things, like in the very old days, there were mirror world people who just thought dark matter was a copy of the standard model. Then afterwards, some people in this room sort of popularized the idea of sort of connecting the asymmetries between them. And that's basically just 2 types of approaches to get similar number densities. And then eventually you try to explain why the masses are similar. These days, you can't do an exact mirror world anymore. You have to sort of tweak it a little bit. You can sort of try to use coupled CFDs, dark matter unification, blah, blah, blah. And amusing random thing is there are of order 700, 800 papers on asymmetric dark matter, and there are of order 7 to 8 papers on all of this on the right-hand side. So for some reason, trying to solve this problem entirely is not particularly popular, but such is life. So if that means, does that mean that we have to take, if at least from my point of view, we have to take this somewhat seriously at least, does this mean that that mass of dark matter is around a few GeV? We should ignore everyone who tells us, oh, we're looking for masses of dark matter less than an eV or heavier than 100 GeV or something like that. And of course, I like other dark matter candidates, and so the goal today is at least to give a second option to sort of asymmetric dark matter type models. All right. So the idea is pretty simple, which is you just start off, something gives you a number of baryons, something gives you an energy density of dark matter, both of them very different, maybe like 8 orders of magnitude different. And then what I'm going to do is couple a scalar to the dark matter and baryons such that it basically just acts as a scale. It just weighs how much dark matter there is in the universe, how much baryons there are in the universe, and then the finite density potential will just minimize everything so that the 2 energy densities are about the same. Right? The idea is just a standard sort of relaxation approach to the problem. Okay, so just to take a concrete example, the idea is, let's just say the dark matter is an axion-like particle. It gets a mass from the confinement of some dark sector, so its mass is like lambda dark squared over some FA. And all I'm going to do is add 1 new particle with 2 couplings. One is I'm going to couple it to the g squared of QCD, and I'm going to couple it to the g squared of this dark confining sector. That way, as I vary it, it changes the QCD gauge coupling, it changes the dark gauge coupling, and so it changes the proton mass at some level. And my claim is, one new particle with these two couplings solves the problem. That's all. Okay, so let's see how that's the case. Well, dimensional transmutation tells you how to go from gauge couplings to the mass of the proton, or the confinement scale. And because the gauge couplings appear in your Lagrangian like this, and so dimensional transmutation sort of takes that phi and exponentiates it. And basically by choice, I'm just going to say, well, I put some order 1 coupling in, times the QCD scale, some order 1 coupling times some dark scale, and by chance I'm going to choose a minus sign instead of the plus sign for the other guy. Basically, this is how you weigh things, is as you increase the mass of one guy, you decrease the mass of the other, and so you're going to have to balance the two. And so at this point, you just did.
Just to understand, the negative coupling with the field strength squared was due to, it's still, asymptotic, it's still confined here in the dark
Yes.
QCD, but the negative sign there is how did you get that?
Yeah, so you can ask, let's just answer, how did I get these couplings to begin with? Which is, you have some heavy particle whose mass depends on phi, and then by beta functions, well, this is some Taylor series, but you get some log of the mass of the particle. And so the question is just, as I increase phi, do I increase or decrease the mass of the particle? Here I increased it, here I decreased it. Of course, this is a Taylor series. Eventually, you're going to have to take the full beta function, because of course you can't take gauge couplings negative and all that stuff, right? And so that's actually exactly the UV. Of course, well, anyone who's done SUSY knows that if you integrate out particles, you don't quite get exactly this coupling. You get some mass to the beta function type stuff instead. But all this math I'm going to go through works for that just as well. It's just that exponentials are slightly easier to deal with right now. And so I'm just going to keep it like this, with keeping in the back of our mind that we're not going to any limit where the gauge couplings really run to like change sign or anything crazy like that. Yeah. Okay. So the idea is, well, we know how the baryon and dark matter masses depend on phi. Let's just mass times the number density. Let's minimize this. Derivative of the first term pulls down a c over f. Derivative of the second term pulls down a c dark over f. And so what you see is, well, that's rho baryon minus rho dark matter equals 0 with some order 1 numbers. And so you just relax to a point where the two energy densities are equal.
Sorry, Vincent, why isn't there just a normal, vacuum potential?
So you want to know, why did I not write down a mass term here? For phi, you mean?
Yeah,
or
or just some potential for phi, that you'd actually, like lambda QCD to the fourth of phi for each sector.
Great.
Like that.
So for now, I'm going to ignore it. I will actually, the last sort of 4 or 5 slides of the talk will actually write down the theory that will cancel the mass term to a sufficient degree.
Okay.
Because it turns out, like, if I just put SUSY at a TeV, you're off by like 3 orders of magnitude in terms of how large the mass potential can be. And in fact,
I mean,
as soon as you say this is larger than the vacuum piece, you know you have a hierarchy problem, right? Like, and so you have to solve it to some
yes, right.
way.
That's
So yes, I actually have 3 or 4 slides at the end to actually explain how that cancellation happens. But for now, let's just say there is a cancellation and see what happens first. Yeah. Okay. Great. So my claim was, in some sense, a very nice and simple idea. Light scalar, new scalar, 2 interactions, and you solve the problem. So let's see how this relaxation happens in our toy model. Because, right, everything is, this is a cosmology problem, so we have to look at the cosmology of the solution. And so you can just go through, solve the equations of motion. And what I'm going to do is just assume that, for example, maybe the QCD scale was 1,000 times, 100 times larger than what it was. And so actually, and it's being relaxed down. And so this starts off large, this starts off small. This is eventually shrinking, this guy is eventually raising up. And so at least the early point, when you're first starting to relax, the baryons are all you care about here. And so you can just ask, how does solving this equation look like? So there are basically three regions, which is, it starts off in a frozen out region. There's a pseudo slow roll region where this thing is actually relaxing to zero, sort of its equilibrium value, sort of not even oscillating, it's just sort of pseudo slow rolling. It's an M of order Hubble. And then eventually you relax, you hit the point where they've been of order 1 the same, and now they oscillate here. Okay, so first stage, frozen out, quite simple. Everyone has done this at some point in their career and said, okay, Hubble, it's an overdamped harmonic oscillator, nothing is moving, Hubble is huge, the mass is small, right? The mass is of order sort of baryon number, well, m squared is of order rho baryon over f squared. What happens when you try to solve this and when the mass is of order Hubble is, well, schematically, well, you kind of have, the math is uninteresting. Schematically, on this side you get 1 over t squared. Phi is only changing logarithmically because it has an exponential. If it changes faster than logarithmically, things are going to change extremely fast. And so it turns out basically what happens is you go through, solve it. QCD scales like 1 over scale factor during this regime. And throughout this whole regime, the mass is of order Hubble, right? Because mass squared is of order this guy, which is 1 over t squared. Hubble squared is of 1 over t squared. And so m of order Hubble, in fact, including order 1 numbers, the attractor solution is mass equals to Hubble. So kind of amusing. But basically all you need to know is during this regime, the QCD scale falls like 1 over square root of temperature, or time, 1 over temperature, 1 over scale factor, so that the baryon energy density in baryons disappears like radiation. Mass is really equal to Hubble throughout this entire time, from beginning to end. And amusingly enough, the kinetic energy in this phi field is half that of the baryons. So you get another guy that's randomly of order the same energy density. Yeah.
Sorry, I'm just having trouble following. So is the temperature way above the QCD scale? Is it in the weak regime or?
Excellent. So let's say, all I'm going to do is say, let's say you have a radiation dominated universe and say that the temperature is, let's say, lower than the QCD scale so that I can treat the baryons as non-relativistic. And then what happens is the background radiation is diluting like t to the 4th. Baryon energy density is also t to the 4th. In particular, its mass is diluting like 1 over temperature, or diluting like temperature. And so m over temperature is constant. So if it starts off non-relativistic, it stays non-relativistic.
Sorry, this is all happening after BBN?
Excellent. No, we're going to be doing this all before BBN.
And you're heating again.
And then we're going to have to reheat. So yeah, you're getting to beyond the toy model, but yes, there's going to be you're going to need an entropy dump for several reasons, but yeah. Okay. And then at the very end, the dark matter potential becomes just as important. It oscillates around its minimum. Since its mass is proportional to some energy density, or mass squared is proportional to some energy density, standard thing of just energy density is just mass times some number density. Number density goes like 1 over a cubed. The mass goes like 1 over a to the 3/2. And so you get the standard, pretty standard
Anthony,
scaling
at
here.
the very start, but your dark matter also carries a charge, so it's not annihilating away.
Excellent. So it could, as long as its energy density is mass times number, then you're good. So you could have equal numbers of particles, antiparticles, could have all particles and no antiparticles, doesn't matter, as long as it's non-relativistic.
Oh, it's already non-relativistic.
Yes.
I see. Okay.
Or
So
more precisely, it's non-relativistic when the relaxation
Yes,
ends.
right.
It doesn't even need to exist as a particle. It could be like an axion-like particle whose mass is smaller than Hubble at the beginning, as long as by
it
the
has
end.
no chance to annihilate at the end. So
Yeah.
that once you
That's right. So this is like post freeze out and things like that. Yeah. Okay. Great. And so that's basically it.
Sorry, what's that 1 over a to the 4.5? Can you say that again?
So the 4.5 is right, standard WKB stuff. If you have a guy whose mass is changing as a function of time, the way its energy density dilutes is just m as a function of time times n as a function of time. n goes like 1 over a cubed. Mass squared is proportional to energy density, which is at this point non-relativistic. The relaxation has stopped, so that's a cubed. And so halve that a cubed, so that's 1.5. Add to the 3, 4 halves.
So at the end of the day, you're getting very light scalar field coupled to T
Yes.
trace of.
Yeah, and so, yeah, you're gonna get to why this is a toy model and how the standard model is gonna have to be different. Yeah.
Didn't we need something that went faster than 1 over 8 to the 4th for the Hubble tension?
Yes, but unfortunately, I don't think you can change the mass of the baryons at the same time. That's a little too late. Yeah. Okay, so either way, this is a quick story. Scalar field starts frozen off, falls off like logarithmically, and eventually dilutes away. Or in terms of the baryons, non-relativistic, 1 over a cubed. Its mass is being adjusted like 1 over a, and then it ends. Okay, so I said this was a toy model. What do you do? Well, what happens with the standard model? Well, first thing to note is it's very excluded if you try to do this straight up with the standard model. Standard state of affairs for model building. And then the next one is, it turns out finite temperature effects are quite important as well. Even if your temperature is below that of the proton, finite temperature effects can still be more important than a rho baryon. Okay, so there are several ways of saying that it's excluded with standard model. Well, one of the things is this works everywhere, anywhere and everywhere. We don't have 5 times more dark matter energy density than us on Earth. We're screwed. You can be more precise in saying, well, neutron stars have it even worse than us, or even fifth force, blah, blah, blah. Either way, a massless scalar with couplings that are less than Planck coupled to us tends to be bad news. So simplest thing to do is to do what we should have done initially, which is add a bare potential for your scalar. And what you can just say is that, well, at late times, right now, this thing is large enough that it just fixes us in place. But in the early universe, things were much denser than we are today. In fact, they could have been more dense than a neutron star. And as long as this thing is such that today it's important, nothing changes. In the early universe, it's small potatoes, then you're good to go.
What kind of masses is Phi going to have today?
Order EV.
EV.
Yeah. So, well, you can get it's usually above an EV because as soon as you start getting fifth force constraints that are weaker, force it to be weaker than gravity, you're really
But that's
in
like
trouble.
1,000 TeV cutoff or something. A
Yeah.
standard from loops. If you
Yeah,
take
that's
this-
right. Yeah, so like I said before, you're gonna have to solve the hierarchy problem there.
So
Yeah.
I think I'm not following this cosine. So I thought this was coupled to this is not
Whoops.
it's not a compact
Yeah.
scalar.
So I did not write a compact scalar, and so the only reason I wrote a cosine is I need there to be multiple minima, because the fact that one of the minima has a proton mass that's near the right value. So maybe I have 20 minima. They're logarithmically distributed. Well, because the proton mass is an exponential, you say each as I go 2 pi capital F here, I change the proton mass by a factor of 10 or something. And so that's basically that's why I wrote a cosine. You could write a more complicated thing, and whatnot. Yeah. Okay, so the idea being just, in the early universe, you relax towards its minimum. Eventually, your temperature decreases. These wiggles become important. You fall into the nearest wiggle. End of the story. So, simple idea. As long as I choose the value of the cosine potential correctly. So you can get around that, and then you just now have a handle to fiddle with what its mass is, and so I can just choose the right mass such that it's not excluded. In particular, get around things like fifth force bounds. The next are temperature-based effects, and the annoying thing is that quantum mechanics does whatever it can. In particular, if you tell it to scan just the QCD scale, RG effects, and in fact going through the QCD phase transition, or QCD confinement scale, you'll generate order 1 couplings to things like alpha E and M and things like that. And it turns out this is actually, even though you have to go through a lot to get to here, it's going to be still changing alpha E and M can be more important on the energy density of your universe than rho baryons. In particular, what you can do is calculate the free energy dependence, which comes from an electron loop with a photon here, 2-loop diagram, and calculate it. Turns out at high energies, this 2-loop diagram is a 1-loop diagram squared, so you don't even need to work hard to do this. And you get something that's basically 10 to the minus 6 times t to the 4th. Now, turns out, unfortunately, rho baryon has a 10 to the minus 10 number density, which is a bit smaller than 10 to the minus 6. And so if you just ask, when does this 10 to the minus 10 here, the rho baryon eventually win, right? Because it's diluting like matter as opposed to radiation. It's not until BBN happens that you're even more sensitive to the rho baryon than you are to this just 2-loop effect.
Sorry, can you say again, where are you getting, what's the effect that's giving you the coupling to S squared?
To here?
Yeah.
It's basically, well, this is basically you take this coupling and you go through the QCD confinement scale,
Yeah.
which to 0th order you can say, well, it's a dilettante-like.
And your stuff is all happening after that, and then you're doing an
that's
entropy
right.
jump later. I see.
And so I could very finely tuned choose a coupling to F squared that then cancels this exactly, but this comes from, for example, the fact that the kaon masses depend on the QCD scales. You transition from the to the pions away from the quarks at the confinement scale, blah, blah. And using some dilettanteology, you can sort of guess what it can be roughly.
Don't you also have a UV contribution from this?
Yes, and a UV contribution.
There's also a UV, which is logarithmically divergent.
Yes. And so,
There's a quark loop, there's a quark loop, where the gluon, there's
But it has an extra loop factor, but it's,
but a log.
sorry,
there.
there's a log.
it has a log.
There's a log.
Yeah, and so you have to just see which one is more important.
And so I have another
Yeah.
question. So if I were to try to engineer this phi dependence of the kinetic term through a threshold correction, let's forget for a moment phi. I
Yeah.
want to scan a big space, a
Yep.
big variation of lambda QCD, and this variation of lambda QCD is some threshold correction. I mean, the real lambda is going to be the power of the beta times some smaller power of
Yes,
the threshold, right?
that's right.
So this mass would have to change quite a lot.
You either need a lot of them or you change one guy a lot.
You either need a lot of them. Yeah, you're saying you need a lot of them, but then
Yeah.
you blow.
Then you get Landau poles quite
Yeah,
close.
exactly.
Yes, that's right. And so actually changing a large amount, like maybe you can change like 10 or 100, but if you really want to change, like what you really want is like, oh, change the QCD scale 10 orders of magnitude.
No, I
Then it's-
understand, but
then
if
it's
you have your cross of the Landau pole, you have very many of them, and as their mass changes, you
Yeah.
have a huge threshold correction that
Yep.
drives down
Yeah.
to a small value over a small range of running. I see.
Yeah. And so, yeah. In the full UV completion, Landau poles are going to be quite close if you really want to live in the exponential limit. Of course, you could always, yeah. Okay. So, okay, great. So, yeah, 2-loop diagrams turn out to be annoying. And so this is, well, there's several reasons, but this is yet another reason why you need something like an entropy dump, because standard cosmology doesn't cut it. Okay. So what we have to do is basically what Nima guessed a little earlier, is you need an entropy dump of some sort, which is you need some energy density in phi at early times that eventually decays and reheats the standard model. As everyone knows, you don't really reheat anything, you just, the early decays make the standard model even hotter, just not the standard red shifting. And so the temperature of the standard model is not too scale factor dependent and eventually falls off here. But meanwhile, rho baryons do just redshift like a cubed. And so you go back, sure, maybe at MEV here is when you finally become important, But if you go back early enough into an entropy dump, eventually rho baryon is just larger than t to the fourth, not even 10 to the minus 6 times t to the fourth, it's just larger than t to the fourth. And so, great. So this is basically what you need at the EFT level to get the model to work. You need to scan the baryon mass, scan the dark matter mass. An amusing thing, since Ricardo brought it up, is all this stuff is beta function dependent, which means the factor of 5 is actually something like 5.14. And so that ratio of beta functions should reproduce this 5.14 to within a percent. And so you have an integer level of precision to try to get this thing to work, and to the percent level. And so it's actually kind of miraculous that you can write some UV completion which works with it to the percent level.
Without having a lot of fields.
Without having like a ginormous number of fields. Yeah. And in fact, yeah. Okay. Great. So just some random values, doesn't really matter. Just mainly chosen to get things to work. So the way the cosmology works is you start off, Hubble is larger than the mass. Something has done baryogenesis that gives rho baryons much larger than t to the fourth. Affleck-Dine does this for you. In fact, they complain about it in the abstract of their Affleck-Dine. They say they get 10 to the 3 instead of 10 to the minus 10 times the number of particles, which actually, if you think about it a second, you'll realize that that gives you rho baryon larger than t to the fourth as a starting point. So it's quite easy to get more dark matter or more baryons than t to the fourth. And then you start off, it's non-relativistic, eventually Hubble equals mass. And my scan error field starts to relax, the QCD scale in particular. And QCD falls like a to the minus 1 over a until rho baryons and rho dark matter are about the same. And they cross, you get to within a factor of 5 of each other, and then they stop adjusting at some relaxation time. Sometime after that, the bare potential becomes important and nails you to a point, nails down the proton mass and the dark matter mass. And so now at this point, you stop caring about finite density crap. And then after that, eventually, you get reheating where your entropy dump just deposits everything into the standard model. You get some temperature that's above BBN, and then standard cosmology from there.
Don't you get also some tumble-fly dark
Yes,
matter from this?
that's right.
From this
And
alignment?
so there's two things that can happen. So in between when you reach the rho equals rho point to when the confinement, the bare potential becomes important, it's diluting away faster than radiation. And so its energy density is going to be less than that of the baryons. But even if this happened at exactly the same time, like its starting energy, kinetic energy, was a half that of the baryons. And so you get an extra field whose energy density is half that of the baryons, and then you have the rest of it in dark matter. So you have like 4.5 in dark matter and a half in this weird scalar, which, depending on your value of f's, may or may not decay through that f squared coupling. So, or in particular for this value, I chose so that it did decay. Okay. Great. So constraints, basically, the coupling to nucleons give both stellar cooling and fifth force. Those are the two things you tend to care about when it comes to g-squared couplings. It can decay into photons, like I said, and depending on your parameter space, it may or may not be important.
What are your Fs?
I took Fs of about 10 to the 7 GeV and masses of about an EV. Now, then there's a bunch of alphas and whatnot to actually get to and overloop factors to get the coupling in front of.
It's low enough so it's not free streaming out of the sun.
We actually do is, well, we chose a parameter such that it's barely not, even if you let it free stream out of everything, that its energy loss or energy transport is less than that of the standard model, and so it's unexcluded, or that's not an issue, yeah.
It's 10 to 7 that coupling, but it's secretly like a 10 to the 9.
Oh,
Yeah.
oh,
Right,
sorry,
because there's an
sorry,
alpha,
sorry,
there's a
no,
loop
sorry,
factor.
I forgot about the rest of the part. Sorry,
Yeah.
yes, okay, now.
Yeah, due to alpha and loop factors, it was chosen, well,
Okay, sorry, yeah, I forgot about the 32 percent.
okay. One other constraint is kind of amusing, is rolling on a bumpy potential has parametric resonance instabilities, and so you have to be careful about that. Fun stuff to work through if you've never done it. Turns out this is actually an annoying issue if you, that places constraints. Of course, you can model build around it by saying this is temperature dependent and blah, blah. So at least in the way I wrote it, there's actually not a whole lot of parameter space available, at least for its coupling to QCD, which folding in everything turns out to be about 10 to the 12 or so. I chose the data point just to live on the edge because that's always more fun. But the mass can actually vary by a lot, which makes it harder to look for depending on where it lives.
Sorry, see, what's the parametric resonance point again?
Okay, so the idea is just that if you're rolling over a cosine potential, and you can just ask, okay, very quickly. If you have V prime is of order some cosine potential, cosine pi over f, which if phi dot is a constant is like cosine phi dot t over f. And this looks like you're basically just oscillating around some term, which actually looks like if you look at a massive particle decaying into phi, it has the exact same equation of motion. And so it looks like, at the equation of motion level, it just looks like a heavy particle decaying into you with a massive order phi dot over f. And Bose enhancement can really screw things up if that becomes too fast.
But what inhomogeneities are we creating in what?
Oh, in phi. And so this is just looking at, there are some K modes.
Why is that bad?
Because those inhomogeneities can suck out energy, which then stop you very quickly. Because I assumed my only friction term was Hubble.
Sorry, I got it.
And so
It's that there's a faster way of losing energy.
there's a faster way of losing energy through inhomogeneous parametric resonance. Yeah. Okay, great. All right, so let's get to Nima's question about how do you get the vacuum potential small. And I actually only know of one way to do this, which is somewhat unfortunate. I like having more than one tool in my model building tool house. And so it's actually pseudo-Goldstone bosons of Zn symmetry, which is start off with a PNGB, a periodic scalar, and make it non-linearly realize a Zn symmetry. So it is equal to itself plus 2 pi, but everything about its potential is symmetric at the 2 pi over n level. Because of this, I can write its potential as just some sum over some function of phi over f plus 2 pi k over n over some k from 0 to n. The reason why I wrote this like this is because it becomes very clear that this is looks like a Riemann sum. And in particular, this means that as I take n to infinity, this turns into an integral that is independent of phi, right? It's an integral over an angle. Your initial and final values don't matter. And so this is just saying as n goes to infinity, it becomes an exact PNGB again. Great, but why does this help us? It helps us because, all right, Euler and Maclaurin sort of had nice theorems involving Riemann sums. In particular, if you look at the potential for phi is entirely coming from the error between the Riemann sum and the integral, and they have some nice properties. Basically, if that function f was analytic, then or if there's a strip around, that means there's a strip around the real axis where f is holomorphic, and they just prove that there's a bound on it, and it's exponential in n. So it's surprising that as you take n to infinity, the mass goes to 0, the potential goes to 0, exponentially fast in n. Not polynomially, which you might have expected. It goes to 0 a lot faster, exponentially. And the physics language of this is basically, as you head off to complex scalar values, if you get massless particles, that's when you start running into non-holomorphic behavior. And so basically your distance to getting massless particles is what determines this exponential.
Sorry, answer.
Yeah,
So the limit where n goes to infinity is where this discrete becomes a continuum.
yeah.
Right?
And so the potential goes to 0.
And you can infer that the approach to Goldstone, masslessness is exponential.
Yes.
It's not power-like.
It's not power-like,
Yeah,
which
how
is
do you see it right away that it's not power?
excellent. So let me just write the physicist proof of this, since so very quickly, I'm basically out of time.
It's
but-
some Wilson.
No, it's going to be some EFT argument,
Okay,
which is why massless particles will screw it up. So whatever, you have, let's say, n copies of QCD, n copies of some scalar. You couple your scalar, you have some Yukawa coupling, and you see, to write a mass term, you need phi to the n because of the Zn symmetry. But every time phi appears, you have a Yukawa coupling. And so the EFT way of writing down this mass term involves y to the n, phi to the n. And so it has to be exponentially suppressed. As long as y times f over m is less than 1, or in other words, you don't have massless particles. If you have, in particular, as you change the vev of phi, if you get massless particles, you don't have some nice analytic function, and so you don't get the nice exponential convergence properties.
There's normally, this is like generating your phi to the n by, well, like your model, like
Yeah.
integrating a big chain of stuff.
Yep.
And I think you're saying that there's what we normally call the UV contribution that goes like y to the n, like we say.
Yeah.
Normally we worry about IR contributions, non-analytic IR things as well, which
Yeah.
are much, much bigger, but you're stipulating that can never happen, that
Yeah.
nowhere as you go around does anything ever become light, so the IR enhancement that we normally expect
Yeah.
and get in various models, so is not there. So it's you're just getting the
Yeah.
the coupling.
And just super quickly, since I find it amusing, since I really do have negative time at this point, I'll write something that, using the Zn approach, that you can't even do with supersymmetry, which is I'm going to remove the potential for the axion, which you'd say even in supersymmetry, you can't get rid of non-perturbative corrections. And so if you just do this what I said here, n QCDs, make the axion non-linearly realize the n QCDs, you get n copies of the standard potential, each with slightly displaced, and you just add them all up. What you get, this potential is analytic, mass gets exponentially suppressed. Do some math, and it turns out it's exponentially suppressed by mu over md to the nth power. Sort of the fact that if you take theta equals pi and mu equals md, the leading order of contribution to the pi and mass is mu minus md, it's 0. And so this is in some sense, your distance to, in some complex plane, to the massless particles. Okay, great. But as long as you have, I don't even need to know the analytic form here. As long as I know that there are no massless particles, as I vary theta, it will be exponentially suppressed. All right, so conclude, I find baryon dark matter coincidence to be very surprising. I think people should study it more. And very amusingly, the model turned out to be too observable initially, and you had to work around it. So I think that's always a good sign. All right, thanks.
Question?
Hi, may I ask you a question?
Yeah.
So, when you're adding a bigger potential, does this mean we need to tune the initial condition of phi? Because otherwise, I just worry whether it will relax to not the minimum point, but the second minimum.
Excellent. So at very high times, let's see if there's. At early times, the potential looks like. Okay, so at early times, this is what the potential looks like, right? It's the finite temperature piece is so important that you don't even see wiggles on it, and you just relax towards the rho equals rho. And then only afterwards, after you relax there, do you fall to your nearest minimum. And so as long as there is a minimum nearby, then you will roll to it. And hopefully the difference in proton mass between here and here is not more than order 1, and so the order 1 equal stays order 1 equal. Because if I wrote this and it had 1 minimum, I'd relax at the early universe and then fall to a random point with nothing being equal to each other, which is why you kind of need the unfortunate fact that you have more than 1 minimum.
You have questions? And you needed Susie at 1,000 TeV or something?
Yeah.
To keep the mass naturally lighter than an EV.
Yeah.
Yeah, and also I have another question is, you said to avoid the coupling from thermal contribution from the 5 square, then you need to make the heating happens later, very late. So does it mean we need to also need to tune the coupling between photon and the step?
Well, I think what you need is you need an entropy dump of some sort, which means inflaton decayed into some other guy. Well, simplest way is it decayed into some other guy, not into us. And then eventually that other guy decayed into us.
Yeah.
And then in the meantime, things like atomic dyne baryogenesis happened.
Thank you.
Can you remind us, answer just quickly, what's the conventional anthropic explanation for the?
The conventional anthropic explanation is, what is it? So you're going to need, well, you hold everything else fixed, and then you say, fixing perturbations, you need enough time for perturbations to grow and form structure.
Yes, thank you, yeah.
Of course, you know, there are a lot of caveats, but
Yeah.
that's the basic idea.
Thank you. Now for the last speaker of the day, Marcus Lutti.
Wow. How much time do I have? Do I have positive time? Okay.
40, with reserve 40. Yeah, if I was saying, I mean, we are perfectly time.
Okay.
We are
Yeah,
3
yeah.
minutes ahead.
3 minutes, wow.
Yeah.
That's amazing.
Yeah, Massimo.
It's imposing discipline.
Yeah, just the question.
I can do this. I can do this.
He's
So I
hungry.
can just share my screen.
He hasn't had his first meal of the day yet.
Yeah. The next speaker would be eaten.
Yeah. Okay, so this is working, yes? Okay, all right, so it's great to be here, amazing. This is an amazing audience. So I just have to make a few remarks. I'm gonna be quick, maybe there'll be more stuff at dinner. But actually what I'm gonna say could be said about a number of people actually in this room. So I have to tell you something very weird about myself, is that the first time that I wrote a paper with someone who was more senior than me was when I was a professor at Maryland and had been there for a few years, and it was Ann Nelson. Okay, that was the first time I wrote, including my advisor. So the people, some of the people in this room were my mentors.
Didn't you write a paper with those guys in, sorry, I forgot, in Montreal McGill when you were in Berkeley?
Actually, you're right.
That was such a good story.
I destroyed my birthday.
I don't want to make it about myself, but the point
Well, I
is-
didn't forget.
the point is-
You see, but you see, 60, I am forgetting the names of.
Yeah. No, but what I wanted to say, Ricardo was actually one of my first mentors. And he would not, exactly, he doesn't believe me, and I understand why
You were my
none of my,
mentor. You were
none of
my
my
mentor.
mentors would believe that I was a mentor because, that they were my mentors, because of course I disagreed with every single thing that they ever told me.
We're gonna
okay?
talk about that at dinner.
So, but it's really true, you know, we met for the first time, we were both graduate students in Cargès, and there was this really annoying Italian guy sitting next to me blowing smoke into my face. Every time I started, he asked me what I was working on, and every time I started to say something, he would exhale a whole bunch of smoke into my face from his cigarette and tell me, I know. But then, we were postdocs together in Berkeley.
I stopped smoking.
And that was really an amazing time because my fellow postdocs and mentors were Ricardo, Raman Sundram, Hitoshi Moriyama, and John March Russell. So these are the people. I should have listened a lot more to more senior people. I wrote a bunch of pretty crappy papers. My first decent paper was with John March Russell at Berkeley, and then later I managed, fortunately, we didn't kill each other. We actually wrote papers together. We cooked together much more often than we've written papers together.
Yes, we haven't.
Yeah. So, but
We shared
anyway.
bread. We shared bread.
We shared a lot of bread.
But that's true that when I got to Berkeley, it was the same thing. It was just you and Raman discussing.
So I mean,
I learned so
Berkeley
much
is really
from them.
where I matured as a physicist, and Ricardo is a very, very big part of that, and so it's really amazing to be here. So what I haven't
You call
matured,
unification.
yeah, you will have
No,
to
so
judge.
important. Such as an amazing paper, TB Tau. Who knew? They can actually got 10 betas, 50. It's amazing.
Yeah.
Just-
So you'll have to judge to see whether I actually have matured. So I'm going to take a chance. You were complaining about 100-page papers. This is a 0-page paper. It's not, okay? So I'm going to state a theorem. I'm going to give the proof, and then I'm going to give some counterexamples. And then I'm going to say a lot of profound things. Okay? So that's the outline of the talk. All right. Okay, so the subject is this recurring subject. It's also a related, this question of symmetries that we don't understand where they come from. We know that fixed points, Wilson taught us to think about quantum field theory in terms of flows, and their fixed points are very special kinds of field theories. And what we normally say is that conformal field theories are these landmarks in the space of theories. By studying them, we can start studying the space of all theories, okay? But this leaves out a little question, which is, why are we talking about conformal field theories, okay? Because the fact that they're fixed points means that we have scale invariance, but very generically, in many, many situations, when we have Lorentz invariance and other things that we want in a quantum field theory, we also get conformal invariance, okay? And so there are a lot of partial theorems connecting these together. So in 2 dimensions, there's a complete answer, but in general dimensions, and in particular in 3 dimensions, there's essentially nothing known because there are a lot of counterexamples. Okay. So there are many, so I'm going to think about this in the language of flows, and just to orient us a little bit, so there are many, many, many examples, especially in 3D, where we have flows where in the UV we have a scale but not conformally invariant theory, and it flows to a conformal theory. Those things are a dime a dozen. But you can ask, what about the other way around? Is it possible that in the UV I have a conformal field theory, and I have flows, and it goes to a theory that is scale invariant but not conformally invariant? Okay, does this ever happen? Okay, and I claim that, so I don't actually know, well, I'll talk about counterexamples at the end, so I won't say anything about this, but the theorem I'm to prove that is under certain fairly general assumptions, this doesn't happen. Okay, that's what I'm going to try to convince you of. And then I'll give you the counterexamples. Okay? All right. So what are the assumptions? I'm going to say precisely what the assumptions are. I'm going to assume that there is a RG flow that has both UV and IR fixed points. Okay, so that's basically that picture.
Sorry, can I just interrupt?
Yeah.
So this is not covered under the scale invariance implies conformal invariance? Or you're
So
saying
there is no,
there's no statement of that sort in 3 dimensions, you say?
there's no statement that I know of in 3 dimensions at all, at any strength.
But the
okay?
stuff that you guys did, Polczynski, other people, was 4 dimensions?
That
even
was in
dimensions?
4 dimensions, and there were quote unquote loopholes. So it's, there are,
And 4, 3 is even odd, or is it really 4? I mean,
I think it's really
Four,
four.
because Maxwell is conformal in 4, right? That's the point. That pre-Maxwell is not conformal in 3 dimensions.
Yeah.
In
I mean,
any
in
dimension.
higher
it's not-
dimensions, it's a little bit, there are very few field theories, right? There are few interesting field
So it's
theories.
not even odd, it's just, it's.
Yeah, so really, in 3 dimensions, there's a plethora of flows, and so it's, you know, and there are no general results at all that I know of. Okay, maybe I'm missing something.
So, yeah, I mean, if I can add, in 4 dimensions, there are loopholes, the non-perturbative proof under general condition, yeah, I mean, that's in a sense
There-
loopholes,
yeah.
but there is a partial rigorous
The theory-
result.
the-
If you
the
tailor the
theory-
hypothesis, then there is a more rigorous statement, meaning,
So this is a weaker statement now. You're gonna be making a claim of something weaker that at least you can't get to an
Yeah.
SFT from a.
Exactly, right. And there are many, I mean, the quote-unquote counterexamples, namely the theories that are scaled but not conformally invariant in 4 dimensions tend to be these really crappy, like free theories with stuff modded out and crap like that you don't care about. In 3D, these flows are the most interesting flows. Like, for example, just QED3 in the flowing, things that involve QED3 or gauge theories and things like that, okay? So really, I think the main interest in this is in 3 dimensions, okay? But the argument is independent of the dimensions, you'll see.
Marcus?
Yeah.
Just one quick. So how should I think of CFT to SFT? Is it spontaneous breaking of those generators or?
Well, so I think it's a really, I would say that so you're asking me, like, can I say that somehow conformal invariance is an accidental symmetry or something
Or
like
that
that?
it
Like
cannot be
no,
spontaneously broken?
he wants to see the breaking of, I mean, the group is smaller, so the scale has 4 less generators. He wants to
Yeah,
understand
there are
whether-
less, fewer generators.
It's like a Lorentz invariance isn't spontaneously broken type of theorem. Is it like?
I think it's more, look, when I have a flow, scale invariance is explicitly broken, and it's only asymptotically a good symmetry in the UV and the IR. So I'm not sure that spontaneous breaking is
Oh,
relevant
sorry, you're
at
a
all.
little bit away from some UV fixed
I'm
point or
flowing
something.
from the UV to the IR, it's a big flow, this theory is not at all, the full theory is not at all conformally invariant or scale invariant or anything, it's only at the UV and the IR limits.
Can I ask one final quick question? If
Yeah.
it has a long answer, forget it, and surely someone has thought about this, but one way you could engineer it like holographically would be have something like a ghost condensate in the 5th direction.
Yeah.
Would be, and?
I don't remember offhand what the thing is, let's talk about that later, I don't know. Okay. So, but I'm gonna require a bit more than the theory is conformal in the UV. I'm gonna require that it's also invariant under conformal inversions, right? So this is kind of like the difference between the proper Lorentz group and, the Lorentz group plus, say, parity or something. So, okay, I'm gonna be always in Euclidean space for this talk. So this is an additional discrete symmetry, and in Euclidean space, what it does is it interchanges the inside and the outside of a sphere, okay? So, and you'll see that's actually gonna be super important, okay, in this discussion, okay? And then I'm going to assume furthermore that the flow is generated by relevant perturbations, and also, if I have a UV theory that has this inversion symmetry, every operator will have some parity under this inversion symmetry, plus or minus. I'm assuming that the relevant perturbations have even parity under this. Okay, that's also going to be important. Then the theorem says, that's it. If I have an IR fixed point, which of course I'm not guaranteed to have, but if I have one, it's going to be a conformal theory, not just a scale invariant theory. Okay? All right. So I'm just going to, if anybody wants to go to the bathroom, I'm just going to tell you the entire talk now in one slide, okay? And the rest of it is just going to be fleshing out these points,
So
okay?
Mark, I was just on the previous slide. So what do you mean? Because I thought CFT conformal means that there are inversions, means there are special conformal.
I'm talking about the assumptions are about the UV fixed point.
Right, but what do you mean that it's conformal plus invariant and the conformal
The
inversion?
UV fixed point is conformal, and the UV fixed point also has this inversion symmetry.
So this is a discrete symmetry.
It's a discrete symmetry. It's like, in fact, in
So it's not
the
a special conformal transformation.
in the
we normally say we get the special conformal by starting with inversions and translating and inverting back. But
Yeah.
he's saying you can imagine you
You
only
have to do
have.
two inversions.
Yeah.
In fact, you know, in the embedding formalism, this literally is, you know, the strict conformal group is the proper Lorentz group in two more dimensions. This is one of the improper Lorentz groups. I don't remember which
If
one
you have
now.
a free scalar, what's an example of an operator with odd inversion parity?
I think just like FF tilde in four
Oh, I
dimensions,
see, I see.
things like that.
No,
Okay.
no, it's good. I see.
Okay?
Thank you.
Yeah, I mean, if you just think about, yeah, okay. Okay, so there's sort of some additional symmetry that I'm requiring in the UV, and it's only in this class of theories that I can prove my thing, okay? All right, so what's the idea? The first idea is that we're going to use radial quantization, not just to study the CFT, but to study the entire flow, okay? There's no reason why we can't do that, that's just a quantization. And what the special thing about inversions, why our inversions are playing such a big role, is because in radial quantization, conformal inversions are literally time reversal. They're just taking the time to minus the time, okay, around some arbitrary t equals 0 thing, okay? And what is time reversal invariance? We know that acting on the Hilbert space, so when I say radial quantization, I'm really thinking in a Hamiltonian language, so I have some Hilbert space that lives on spheres and I have a Hamiltonian on it. And if I ask, you know, time reversal I know is an anti-unitary transformation. That means it's essentially a kind of complex conjugation, okay? And the condition that the UV theory is invariant under time reversal is a reality condition. It's basically saying that in addition to being Hermitian, the Hamiltonian is also real. There's a basis in which it's real, okay? And because the perturbations are also even under this time reversal symmetry, the Hamiltonian is real actually all along the flow, okay? And so then, if it goes to a fixed point, it's still real at the fixed point, and so it has this inversion symmetry. So that's the basic idea. Now, if you have questions about any of these things, I have like 3 slides on each of these things, okay? So I'm just wanting to just sort of, so you know this is like the outline of the thing, okay?
So you say that essentially by saying that if you have the discrete symmetry of inversions, then by doing the usual thing, you get special conformal.
Yeah.
out of it, then I see.
Exactly,
So
exactly. That's the last thing, is that, yes. So the last thing is just a group theory statement, is that because I assume that I have translation symmetry, okay, I mean, I have the usual, you know, things, then if I conjugate by an inversion, I get a special conformal transformation, okay?
So Marcus, can you just repeat this statement about perturbations? You said that at the fixed point, it's real because you're in the radial quantization.
Yeah, I'm going to give, yeah.
But normally it's better if you give first the 3 slides, because you're going to present the slides.
I'm going to explain each of these points in great detail.
Okay, but you said a sentence about perturbations. So
Yeah,
the perturbations are real too.
I have a slide on your question.
Okay.
So okay, so if I don't answer it on the slide, then ask me again, okay? Okay, so I'm just gonna go through these things one at a time, okay? And talk about what the possible subtleties are, right? Because remember, there are quote-unquote counterexamples, okay? So just at a very basic level, what is radial quantization? It's just a choice of a time variable, right? That's what I do in a Hamiltonian. And so I'm in Euclidean space, and I just choose the time variable tau, like this, okay? And so it's nice to see a very, very concrete example. Here's my favorite example, 3D phi-4 theory, okay? And if I just define this dimensionless field, and I just use these coordinates, and I just write the action, this is what I get, okay? Everything is dimensionless, right? But you see that the mass and the coupling term have some explicit tau dependence, right? And so the UV limit is tau going to minus infinity, and these terms go away, and I just get a nice massless theory, right? And that's it, okay? All right, there's this thing right here. Well, there's a famous story about this thing right here, right? We know that thing is there, okay? And this theory is kind of my go-to example because we know that if we tune the ratio of these relevant perturbations, to a critical value, this thing will flow to a very non-trivial theory, the 3D icing model in the IR, right? So this is the sort of canonical example to which my argument applies, and so you can say this is a pencil and paper proof that the fixed point of this theory is in fact conformal, not just scale invariant, right? Okay, so, and a more sort of fancy way of thinking about it, which is useful, is to say that the wave functions, if I'm thinking about a Hamiltonian formalism, then the wave functions that I'm interested in are living on spheres of some fixed radius, and since my system depends explicitly on time, it's very natural to use sort of Schrodinger picture where the states evolve in time, like this, okay? And so in 3D 5-4 theory, I can just, work out what this Hamiltonian is, and again, it just has some explicit tau dependence that's related to the relevant perturbations, okay? How much time do I have? Just want to keep track. I know I'm not close, I just want to...
Plenty.
Okay, plenty. Okay, anyway.
18.
Oh, wow, okay. Yeah, okay, so first let's talk about the UV fixed point. The UV fixed point is pretty trivial, right? Because the point is that the Hamiltonian explicitly depends on tau, but if I just take the limit as tau goes to negative infinity, it doesn't depend on tau anymore. So that's it, okay? And so it's useful in that limit to label the states by the operators in the usual way, okay? And these are eigenstates of the UV Hamiltonian. And so, for example, in my 3D 5-4 theory, the theory is a free theory. It has a Fock space, okay? And therefore, the UV Hamiltonian is just a bunch of harmonic oscillators. And you can see that these the state operator correspondence works, namely that if you create states with the A daggers, their eigenvalues are exactly the dimensions of these operators, right? And this 1/2 piece is related to that, conformal coupling piece that exists there, okay? Okay, so there's not too much to say about the UV. Now, the UV inversions, okay, so this acts as an anti-unitary transformation, and what that means is that it acts as complex conjugation, okay? So let me just, since this is something that we usually don't think about, and the chapter on this in Peskin-Schroeder is really awful, okay? Let me just remind you, in quantum mechanics, how does it work? I just have my P and Q operators, right? And so what is this mysterious real basis? The real basis is nothing other than the Q basis, okay? So the claim is that what is time reversal in good old Schrodinger quantum mechanics? It's just complex conjugation of the wave function, right? And so if you look at the Q operator, if you conjugate it by P, you get Q star, which is Q, but P, because P has a minus I in the definition, P star is minus P, right? And so you reverse the signs of momenta and you don't reverse the signs of positions. That's exactly what time reversal is supposed to do, okay? So in quantum field theory, it's the same thing. If I have some wave function that depends on the fields, it's just complex conjugation in that basis, okay? And so a general operator just goes to its complex conjugate, and the UV Lagrange, therefore the UV Hamiltonian is also real. Okay, so in addition to being Hermitian, it's real. Okay, now the relevant perturbations. Okay, so I have some perturbations like this, and when I put them into the Hamiltonian, they of course get some tau dependence that's related to their dimension. That's the whole point. This is generating the flow. And this is the assumption. The assumption is that this operator O is real. Sorry. That's the answer to your question. That's what I mean by having even time or inversion parity. It's real. Okay? So that may or may not be true in whatever theory you're interested in, but that's the assumption. Okay? And so that implies that this piece that breaks scale invariance is also real. Okay, so the whole Hamiltonian is real. Hamiltonian is real all along the flow. Okay, so this reality condition corresponds to a symmetry at the UV fixed point, but it's also just true away from the UV fixed point with these assumptions.
So is your guess, if you don't put this requirement on O, that it is real, that you'll never float a scale invariant theory either? Or why do you
No, I mean,
put this assumption about the flow itself? Beyond the.
you're asking me what happens if I relax this assumption?
Yeah.
I don't know. I have no idea. Okay. Yeah.
Marcus, I don't want to piss you off because I already asked you this question, I already answered probably twice, and I forgot.
This is how we
In fact, you even told me, so the Hamiltonian can always be made real by going to the eigenbasis.
Right.
So here there is a sense in which you're starting from a Hamiltonian unperturbed in the basis of the phi field.
Yes.
And then as it evolves, without changing the basis, it remains real. Is that the statement?
Yeah, so you're exactly right, good, this is a very good point. So there are many possible definitions of star, okay? The claim is that, so the correct one to use is the one that corresponds to physical inversion symmetry in the UV theory, okay? So like in quantum mechanics, this is certainly not the only definition of star, but it's the one that corresponds to time reversal.
Yes, there is the one that corresponds
Yeah,
to you.
and so choosing that to be the case in the UV theory fixes once and for all what star means, right? Because the Hilbert space can be defined in the UV theory, and so now this completely defines what star means on the Hilbert space in such a way that it actually corresponds to time reversal.
Yeah, because you could have started with the P.
Yeah, it could have made
And then
P
you
real.
do PT.
Yeah, I could have made P space be the real thing, and that would be exactly the wrong thing. I could choose the eigenvalues of the Hamiltonian to be real, and then I would say that, every it's crucial that I'm using the star that corresponds to the physical notion of time reversal invariant. And so this is in the UV, so you should really ask this question again when I get to the IR, because you might say, well, is this star the right thing in the IR? Okay, so we're going to talk about that, but that's not clear yet.
But doesn't this mean you're imposing a discrete symmetry on the entire space? Right?
No,
You're away from
there's
the
no, so this is not a symmetry, as far as I know. I mean, remember that the Hamiltonian depends explicitly on tau. So, it's driving, it's like, there's no time translation invariance, let alone time reversal invariance or anything like that. But reality is reality, okay? Like, once it's real, it doesn't become complex somehow, right? Okay?
So this is really just a statement about the real part of your Hamiltonian, because you could have just picked a random Hamiltonian and had the Hamiltonian plus its complex conjugate, and then do the full flow, and then you would get that the real part and the IR will have this enhanced symmetry.
Yeah, I guess that's true. I don't know if the real part of a general Hamiltonian has all the physical properties that a theory should have, but yeah, I think that's right. Yeah, I haven't thought about that. Okay, yeah, so the Hamiltonian, so this is it. This is a simple statement. The Hamiltonian is real all along the flow. Okay, so now let's talk about the IR, okay? And I want to talk about the IR in two stages, okay? So first I want you to pretend to believe something that is not true, okay? So imagine that this wasn't a quantum field theory. Just imagine I had some weird Hamiltonian and Euclidean space that depended on tau, okay? Except that in the UV limit, it becomes independent of tau, and in the IR limit, it becomes independent of tau, okay? That's not what happens. It's not what I'm claiming. It's not what I'm going to assume. But this is going to help me to explain some things about the IR fixed point, and then I'll explain the real situation, okay? So pretend that this is true. I just have some explicit time dependence, and it just stops after a while, right? Like some cosmology, something like that, okay? So the claim is that I can think of this star. This star is a kind of symmetry, approximate symmetry, okay? It's a kind of local inversion along the flow, okay? So let me explain that. So imagine I'm somewhere along the flow at some R naught, okay? I can imagine that R naught is very far in the IR if I want, okay? And so remember that I'm in Schrödinger picture, okay? And so in Schrödinger picture, the operators are just the same operators. The Hilbert space is exactly the same Hilbert space at every tau. The operators are exactly the same. What's changing is which state I have, right? That's what's changing, okay? And so now the claim is that I can think about some kind of an inversion transformation around this point. Namely, I take tau minus tau naught to minus that thing, okay? So I take deviations from that, okay? And under this symmetry, I'm going to take O goes to O star. Thanks, 10 minutes. And so I'm going to claim that this is an approximate symmetry if my delta tau is sufficiently small, okay? And the point is very simple. It's just kind of like the equivalence principle in GR, right? There's some scale over which my Hamiltonian is varying, all right? And if I look at very, very short time scales compared to that, I can just say the Hamiltonian is constant, okay? So if you look at what this Hamiltonian looks like, it's a bunch of real operators with coefficients that depend explicitly on tau, right? That's what's going on. And I'm just saying that if I look at sufficiently small tau, I can neglect the time dependence of the operators, okay? But that means that there's an approximate symmetry of the correlation functions, right? If I look at them at tau plus a little bit versus tau minus a little bit, they differ just by complex conjugation, okay? And this is the statement that this star, really is time reversal. It's not something else, okay? I mean, it's not some formal property or something, because it really does imply this relationship right here. And this doesn't matter how far in the IR I am. Okay, so now, if you pretend this thing, then I'm done. If you pretend to believe this thing, then I'm already done, right?
Because pretend because you're throwing out the possibility of cycles or something like that? Why is that pretend?
You'll see. You'll see. That's my next slide. Okay? Okay? So this is already, you sort of see the idea. You see why star is...
But Marcus,
Yeah.
in a sense, this transformation that is time reversal, so it existed to start with.
Yes.
In a sense, you introduce spurions that break it.
Yes.
The masses.
Exactly. Yeah.
But the action, there's still a symmetry there's still a transformation.
Exactly.
The operator defined
Yeah.
on the states and on the operator that acts.
Yeah. I mean, it's just, you know, you can, if you think of this as an initial value surface, star is just reversing the direction of time, right? It's the operator, it takes operators to plus or minus themselves depending on if they're even or odd under time.
For instance, you could engineer, so the case you're presenting here is certainly not what happens in reality, because this you have to integrate, this is the story that you will...
This is my next slide.
But I'm saying that you could engineer a non-realistic situation where you have a theory that in flat space is not an ordinary translation invariant theory. In other words, that you introduce a tau dependence on the cylinder artificially,
right,
that turns off at a certain point,
yeah.
And then you would have...
Yeah, this would be like a cosmology, right? This would be like some kind of cosmology where this star means that the time evolution sort of remembers the notion of time reversal invariance.
Yeah, but I want to say, you could introduce by hand a tau dependence that is not the one induced by the geometry when you map.
Yeah, exactly.
Okay, so
okay, but let me explain why this is, because I think I only have like 5 minutes or something. But the reason why the pretend is wrong is a very simple physical fact, which is that it doesn't matter what tau is, right? Tau is just where my quantization surface is. H of tau encodes all the information of the flow, everything, every last detail. There's no way it's becoming independent of tau, okay? So let me give you, so what I'm going to present is a physical picture for what I think is actually happening, okay? Let's think about the instantaneous eigenvalues, right? So H of tau is just smoothly changing with tau. At every tau, I can just look at these eigenvalues, okay, eigenstates of tau, right? And I can ask, what does this spectrum look like as a function of tau, okay? So if I am interested in the low-lying spectrum, I expect something like this, right? I expect that as tau goes to minus infinity, it's constant, then it does something, and then it becomes constant again, right? But the claim is, so you might say, all right, great. Here, this is the IR, because here in this IR, all these states here are no longer depending on tau, okay? But I claim it can't have the whole spectrum be independent of tau, because then I wouldn't be able to encode the entire UV flow. And so what's going on is that if I pick this tau naught and I go high enough in the spectrum, there are some very high states that are still rocketing away and changing with tau, right? So now I think you can see what the idea is. So just to say this in a more physical way, if I look at a correlation function like this, and here's my quantization surface, I would expect this to be dominated by the low-lying spectrum of the theory, but if I take 2 points very, very close to each other, I'm going to need to know the entire, many, many states on this thing, and I'm going to be, so the UV is encoded in these very high-lying states. That's the basic picture, okay? And so the basic assumption that we need is that if I look at the spectrum, then the very, very high-lying states are not important for the IR physics, okay? And this is exactly the idea behind Hamiltonian quantization, or Hamiltonian truncation, right, is that you just take a Hamiltonian and throw away the high states. I think, we know that that works in many, many cases. I'm assuming it works in this theory, okay? And so then, how do we define the IR theory? Well, we have to do some kind of an effective theory, right? The only thing that is really scale invariant in the IR is not the exact theory, but it's some kind of an effective theory. So how do we define it? So it's a double limit, and the only way I can understand double limits, because I'm dyslexic, is I have to sportscast them. So I'm going to sportscast a double limit for you. So first, we start with the Hamiltonian at some tau, let's say here. So you pick your favorite tau, and then you pick some delta max, and I just truncate the Hamiltonian at that tau with some maximum dimension delta max, okay? All right, and that may include some states that are also varying with tau, okay, or not. But then I first take the tau goes to infinity limit, okay? So you have to fix delta max, you don't get to change it, but I'm now going to increase tau so much that even those states up there are now constant. They're as constant as I want them to be, right? And then after that, I take the delta max goes to infinity limit to get the full 5 minutes, the full spectrum. Okay, so the claim is that is the correct definition of the IR effective theory. Okay, all right? All right, and this is the thing that computes exactly, limits like this, limits where you scale all the points out to infinity and so on, right? Okay, so that's it. And that's it. Okay, so I've assembled all of the ingredients for you, right? Basically, the idea is that what I had to show you was that this theory is inversion invariant, okay? And I have tried to convince you that, so again, this is real, this thing is obviously real. I've tried to convince you that complex conjugation truly is physical inversion symmetry, and so I claim I'm done. That's it. Okay?
Are you claiming that the opposite order of limits would not define the...
It definitely would not, because if I sit here and say delta max goes to infinity, I get into these states that are going nuts.
Right, but then you send out infinity afterwards.
I don't know. I think this is the right limit way to think about it, right? Because here, this thing here is scale invariant, right? And then I just add more states.
Yeah, I'm not arguing that that's correct.
Okay.
I'm just asking you if I reverse the order of limits, is it now not correct?
Okay, maybe it is. I don't know. To me, it doesn't seem like it would be, but maybe we could talk about it. I don't know. Maybe I'm not thinking about it straight. Like I said, I'm dyslexic, so. Yeah.
So we discussed this some time ago about in the argument that when tau goes to infinity, there are these states that have not yet settled, and they are there's still some dependence on tau. But you're saying I integrate them out, and this will give us effect that go.
Yeah, I think you could worry, because you could worry that somehow, when I take tau really large, not only maybe these states are getting far away, but maybe they're also varying faster or something like that. And so somehow their derivative, there's some sort of an anomaly type effect, that maybe the UV. So I just said I assume they decouple, and that's just my assumption that that doesn't happen. But I don't know, I don't have a better argument for that.
Because there's the possibility that you have because, in what sense, So there is a tau dependence that goes very fast there.
Right.
And as you said, you integrate them out and this becomes an e to the minus tau,
Yeah.
because but then there could be a term like tau over absolute value of tau. Okay,
It's exactly the anomaly worry, right?
It's an anomaly, yeah, but this is a law.
Worry. I think
This is
it's
precisely.
You figure out something
Yeah.
whose entire effect still
Yeah.
looks like something
Tau
local,
over
but
absolute
that
value of
just
tau.
breaks- But that just breaks.
It's just the sign of tau.
Yeah, I mean, notice it can't literally break the symmetry, because you can't tell me
Right.
that that's gonna be not real. So it's gonna have to be somehow, I don't know, it's gonna have to somehow physically change what physical inversion symmetry is. I don't even know how to think about it. But I'm just saying it's an assumption here.
But also, what about cycles? I mean,
Oh, I'm just
Mark-
assuming that it's a fixed point.
Oh, I
I'm just
see.
assuming it's
Oh,
a
you're
fixed
just
point.
assuming it's a
I'm
fixed
just
point.
assuming it's a fixed
Right.
point and trying to prove that it's also conformal.
No, sorry, but if you have a term, let's say that if, so there is something weird in the argument about complex and real, on the fact that this thing really, I mean, probably precisely like an anomaly, you cannot have both. You cannot have the reality and the thing that acts on the fields precisely.
Yeah.
Yeah, there's something, because there's this tau, I mean, if you have a term in the Hamiltonian, it's like tau over absolute value of tau. Somehow this, under time reversal, should
Yeah.
change sign and maybe this comes with a complex.
I don't know.
I don't know.
I really don't know. I mean, I don't know how to, I
So
certainly
this should
know
be-
that this decoupling, I mean, I wrote a whole paper on this. In Hamiltonian truncation, you can worry about whether this kind of decoupling actually happens. So we certainly showed that in cases where the UV is perturbative, which actually includes a lot of interesting flows, it is. Okay, so in other words, if standard decoupling, Wilsonian decoupling works, this truncation is some sort of non-local cutoff, right? Because it's a cutoff on the total energy, the integrated Hamiltonian. But decoupling still works, when we can prove it, namely when the.
No, but it would be interesting perhaps, Marcus, to identify if there is precisely a sort of anomaly that characterizes precisely maybe cases where
Maybe,
it
that
doesn't.
would be, yeah, okay. I know that it doesn't happen in phi, like in the phi cube theory, I think I know that this is true because there the UV is weakly coupled, and I actually know how to integrate out these states, okay? We wrote a whole paper on this. There are some non-local counter terms, but they're still under control of the IR scales divided by UV scales. So I don't think there can be any problem in any perturbative theory. Well, yeah, I don't, at least in that theory, for sure.
So what are
Okay.
the counterexamples then? So
Counterexamples. Okay, so all of these counterexamples are indirect constructions, all the ones I know about. Okay, so I'm going to give you the very, very simplest one, and then I'm just going to say that I think the other counterexamples that I don't know about are like this one. Okay, so this is a very famous flow. There's a flow, so this is not yet, this is an indirect construction, so this is just the first step, this is not the flow. One of the most famous example of an SFT flowing to a CFT that I know of is 3D QED, okay? And that is scale but not conformally invariant. I just turn on a gauge coupling, which is a relevant perturbation, and it flows to CFT, okay? And that was first shown in the 80s, and there have been like a million papers on this, okay? And so I'm really giving just a very basic summary here. The way you can think about this flow is you can just think about saying that, the turning on this gauge coupling here is actually irrelevant at this fixed point, okay? Of course, this doesn't violate my theorem, because my theorem says you can't go the other way, right? That's what, all right? But then you know that, of course, I could also turn on a mass, all right? And I certainly know what's going to happen then. If I turn on a mass, I just go to free Maxwell theory. I'm assuming I'm turning on a mass for all flavors for simplicity, right? And then I can start doing a combination of those things, okay? And this theory, at least in the 1 over NF expansion, you can understand it in terms of diagrams, okay? And it's just some chain of bubble type thing, okay? And so we know that everywhere in this plane, if I add masses for all the fermions, it eventually flows to free Maxwell, okay? All right, at least to all orders in the 1 over NF expansion. I think we know that for sure. And so now you see the problem, right? Because what I do is I just keep going closer and closer to this CFT3 fixed point, and I can get arbitrarily close to it. So at some point, there's a flow that goes from that theory to the free Maxwell theory, and that violates my theorem. okay? So that's the counterexample, okay? But I claim that's not what happens, okay? What happens is maybe a little bit surprising at first. What happens, and this sounds like a kludge, right? It sounds like I'm just trying to save my theorem, but I think it's more than that. What I claim that actually happens is that if you start at CFT3 and you actually turn on the mass perturbation, you don't flow here, you flow to some new fixed point, okay? In fact, let me tell you what that fixed point is, at least for very large NF. So first of all, the words that go along with this is the claim is that the same operator, which is, you know, irrelevant at CFT3, but it's actually dangerously irrelevant at, okay? So I remind you, what is a dangerously irrelevant operator? It's an irrelevant operator that nonetheless, if you turn it on, it changes the universality class of the IR fixed point. And the classic example of this would be some 4 quark operators you add to QCD, which have some discrete chiral symmetry that forbids a mass term. So you don't have a quark mass, but you have a dimension 6 operator, but it breaks all of the chiral symmetries. So instead of having massless pions, you have a gap theory, right? So adding an irrelevant, 1 minute, thanks. Okay, so that's what a dangerously irrelevant operator is. So the claim is that these flows that go arbitrarily close to CFT3, they've turned on one of these dangerously irrelevant operators. Okay, so that's the claim. What is this CFT3 prime? Well, if the NF goes to infinity limit, the reason that this theory is solvable is because in that limit, the CFT3 is just some free theory. Okay, so I can give it a Lagrangian description. It has some weird kinetic term, but it doesn't matter since it's a Gaussian theory and I'm just computing loops, it doesn't matter, okay? And crucially, at that fixed point, the fermions are not charged under this, right? Otherwise, that would be this fixed point, right? If they were so that's the statement that the G goes away, is it, okay? And now you look at this and you say, well, you tell me, what happens if I add a mass term for these guys? They just go away, right? But I don't go to free Maxwell, I go to this, oh, boy, at exactly the wrong term. Anyway, this is obviously, no, just forget about the minus 1/4. You just, so, sorry. Anyway, sorry, you just get this term. I don't know why I wrote this way. You just get rid of this. This is supposed to be F, 1 over box F, okay? All right, so that's what happens in the infinite NF limit. I believe I can actually show that this dangerously irrelevant operator, in the case of QCD, we can understand it because it breaks some symmetries, okay? I believe it breaks the reality condition in radial quantization. So it's actually, the QCD case is a pretty close analogy. Okay, so I've got -1 minute or something. The other counterexamples, there's a bunch of counterexamples in string theory that have to do with these strongly coupled fixed points, okay? So I can have some conventional compactification of string theory